idea of doing.
Yeah.
Anyway, I replied to yes, and then asked if there's any funding, but
Years? Was it every year?
he's a bit curious.
Right.
And he said it's mostly mathematics, but you can easily add physics.
The problem is, well, they had it this year, right?
Now they're not.
No? Okay, so then it would be right before ocean sciences. Right, if they do it in January next year, then ocean sciences in February. Probably people are going to want to get both.
Yeah. Anyway, I'll talk to people to keep it in the loop.
Sure.
And the other thing is that's super severe. So you think he's like a no? Yeah.
So
You have
you told me is that
I have a paper on discretizations with B grid, C grid. Yeah, and C grid is terrible at low resolution. I did baroclinic instability. Just linear baroclinic instability,
falls
not
onto
QG primitive
leads.
equation.
Maybe there's
Yeah,
like some
with
internal
same
lead fraction.
discretizations that are used in
Snow that falls
analysis.
onto leads was getting 0 through the coupler.
C grid is actually pretty
It
bad.
looks like that's not
at
being
baroclinic
accounted for
instability
elsewhere.
until you get to eddy resolve.
And their budget's balanced
So
because their budgets were
Even
computing.
it's not even good at 1 degree. Yeah.
Okay.
They're computing like in and out after that
I mean,
zeroing out had happened.
there's
or
probably a
reschedule.
lot of problems at
So
3 degrees.
the budget, that was
I think
happening
that's
outside of
probably
their
one of
internal
them.
budget conversation.
I mean, just fundamentally, if your boundary current is like 100 kilometers wide and you got
But
like
that's only, I'm a little fuzzy about
And your
leads
grid
versus
cell
open
is
ocean.
3
Because
degrees.
if the coupler sees an
What do
open
you
ocean
do?
fraction,
Yeah, but
there's snow.
that's okay.
Snow
Like
from that.
you can compensate by having high
But if they fix this, we're gonna get more
things
snow,
like that carrying the transport for you, right?
which will
I mean,
give us,
I don't
it'll
think
make us
I don't
fresher
think-
and colder.
I
So we're gonna have to
I don't
melt
think
it.
he's trying to resolve boundary currents and stuff, but like just, I think it can be improved from what he showed yesterday.
You mean the 3 degree?
Yeah,
Working on that is not the kind of thing that would interest me.
yeah, I know, but like, it's just, like, I don't think
Oh,
he's like.
sorry,
he's,
Stu.
I
Attacking
just
you
don't,
while.
when people say, yeah, like, I understand the resolution issue, but I don't think he tested, like, there's other things we could.
Done to try and make it better.
Like, so the years down. None of that.
That low of a resolution is not something that I think about very often.
Yeah, I was just wondering because of the mediate, if you was like that.
It was just dark.
Do you know,
Yeah.
these
I mean,
two
at 3
brands
degrees, you're probably not
presentation?
even resolving hurricane
Oh,
instability,
yeah.
even if it was
No.
a grid.
Yeah. Okay, thank you.
Oh, just because, I usually start with like, looking at the equatorial currencies and blah, blah, blah. And you both had about that before. Thank you. I want to send a picture of both my certificates.
It's different this year.
It's
so-
different. Wow. I have the ultra predictive of what groundhog does what.
Still want to.
That is cool.
Don't pay our taxes with it.
I had not heard of this tradition before last year or entering the getting contest.
How many people are?
11. I mean,
You're
this
the only
one's-
one that guessed right.
Yeah, yeah. I mean, I guess, right.
People
by
were
choosing my
optimistic that
lucky
winter
row.
would be short, I guess.
Yeah, I think I didn't understand it, so I thought I was being optimistic, and I guessed all the all the opposite things.
By the way, that camera responds to motion.
Oh, so I'm
So
here. Oh God, maybe I'm gonna go away. Actually.
You should go away from this.
I started watching yesterday and I kept seeing myself popping up on
So it's
camera.
motion that it was
It's
from?
motion and sound.
Yeah, because I was trying to be really quiet yesterday and it's.
It kept going to me yesterday. Liz Maroon wrote to me and said, hi. Keep seeing you.
Yeah.
Me talking right now, it's pointing at me.
Okay.
I started getting self-conscious when I saw myself appearing on the camera.
Yeah, I'd rather not be on camera all the
Ian's
time.
peering at his screen, so that's showing up.
We just turn it, put something on top like a cup.
So,
It's kind of funny. It's like it is looking at me.
Yeah,
It's good for the
so,
eyes.
so is that indicating anything? Or that's just to be cute because it's an owl? Okay.
yeah, I think the camera's on the timer.
Mm,
Sometimes it pings when people come on and sometimes it doesn't.
it's when people from NCAR join, you can just join, you don't have to request and then it doesn't ping. But when people from outside request and then it makes it worse.
Okay. That's better.
Yeah.
Okay, you want to run the first one then? Sure. I see Rob is on.
Ian will share the continuation of the.
Oh, you want to do the first one?
No,
Okay.
whatever.
Well, you could do it from either. I have it kind of set up here. Okay. We're both in Japan. So I'm showing from this one, sort of watching the participants on that one. I think, Anna, are you gonna run from your own?
Mm-hmm.
So
Oh, I
don't think
can
we're gonna
run.
need either of these until possibly after the break. I think Bill needs.
How's it going? Did everything work out yesterday?
Yeah, we're good.
And everything seems pretty smooth going today?
Yeah, other than the fact that this is a crappy projector, it's all good.
Or we want to get that fixed one day. Well, we'll see. Yeah. If you have any questions or anything, me or Paul, always gonna do the right thing.
Thanks.
So, yeah, have a good meeting.
Thanks.
Sure. What do you?
Still have your.
The national.
It's just an also still has it. I don't know how they managed to have it.
Is that blue thing up in there?
Yeah, I know.
No, the other way, this way. It's from Nashville. What do you want?
It would have taken me an hour to find.
right, everybody, welcome back. Can you hear us online? Can somebody give us a thumbs up, acknowledgement?
Yep.
Okay. There we go, somebody. So welcome back. We're finishing off this morning the Regional Ocean Modeling Group of Talks with our first talk. And then after that, there's 3 talks, starting a session on biofuel mixing and ocean boundary layer characterization. Break at 10:20. 3 more talks on biofuel mixing and ocean boundary layer characterization until lunch. And in the afternoon, we do mesoscale and sub-mesoscale characterization. Our first talk this morning is, Rob Hetland. Sorry, Rob, are you there?
I'm here, and it seems like I've never shared my screen on Google Chrome before. So it's asking me for permissions. Let's see if I can try this again. Microsoft PowerPoint, share, system. I don't have screen recording permissions on my computer. I have to fix it.
Working on it.
I'll work on it here.
Let's see. I think we have this talk.
When he's sharing, will we be able to see when he's sharing the screen?
I'm going to have to log out and log back in again. Do you want to switch to Deepak while I get my technical issues underway, or
We have your talk, and you could drive the slides from here and just tell us next slide, back slide, whatever.
can I? Well, let me upload. Can I send in my most recent one to you guys?
Okay, well, why don't you go ahead and log out, log in again, and we'll just wait for you.
Okay. Sorry about that. I'll be back soon.
If that works.
Everybody here okay? Should I turn that up at all? Is it possible to turn it up?
It is. I can turn it up.
It was a little similar, for me, it was quite, I'm sure. I have to move, I think. On the video the whole time.
That's pretty quick. Let's see if this works now. I've never had my everything like. Can you see this now?
Yes.
All right, here. Let me go into presenter mode. How about that? Can you see that?
Yes.
All right, great. So thanks for letting me join this meeting. It's been interesting to me so far. So I guess this is kind of a like a long time listener, first time caller situation. I know some of you, but not others. And for the people who don't know me, let me give you a little background. I'm at PNNL. I'm an earth scientist at PNNL. Before that, I was at Texas A&M for 20 years, where I focused on sort of small scale coastal ocean modeling, river plumes, estuaries, stuff much smaller than the things that have been discussed here. You know, domains easily fitting within a grid cell. Since joining PNNL, I've been interested in thinking about instead of thinking about how to go down in scale, how to go back up in scale, and so that's why I'm interested in talking to you today. Topic of today's talk is on high resolution regional ocean modeling, coupling ROMs to E3SMs. This is part of a project called Seahorse that I'll explain in a few slides. But first, I wanted to just give a shout out to 2 other regional projects that I'm involved with in kind of the DOE coastal ecosystem. In case you don't know about these, one is the Integrated Coastal Modeling Project. This has been focused on extreme events and climate change attribution along the U.S. East Coast, coupling sort of One of the aspects that's been pretty interesting is coupling land runoff models to an estuary model to look at inundation, coastal inundation. The other project is the Great Lakes Modeling Project, Compass Great Lakes Modeling Project. And that is focused on building sort of a regional coupled Earth system model where we have lake, atmosphere, land, and all of these models sort of running at the regional scale or very high resolution. And so that might be interesting to some of you as well. So back to the project at hand. So the Seahorse Project stands for the Study of Exascale Advances in a High-Resolution Ocean using ROMS coupled to E3SM. It's kind of a forced acronym, and the C has a little hook on it to make sure it's pronounced like an S. It's one of these scientific discovery through advanced computing projects at the DOA Fund. So part of that is you have to have, part of it is a science focused, part of it is computational focused. So we have objectives sort of in both of those directions. So in the science direction, we have focus on improved representation of small scale coastal and open ocean processes in larger scale climate models. We're thinking like river plumes, coastal fronts, meso and submesoscale eddy processes in the open ocean. And we want to think about these in the context of global Earth system models. As part of doing that, we want to design a scientific and technical framework for two-way coupling between ROMS and MPASO, for optional, flexible, efficient, robust, dynamical up and down scaling. So I think the key part here is optional. We see this as a component of E3SM that you could turn off and not, you don't have to run E3SM with ROMS. You can, if you choose, you can do it for a day, a week, a month, but you can also turn it off again and not sort of mess with your long-term 1,000-year simulations at coarser scales. And another interesting aspect of this I'll talk about at the very end is we want to create and evaluate ROMS X, which is a GPU-enabled port of ROMS that exploits the latest HPC architecture. So rewrite ROMS in C++ and use the ARMX protocol to be able to run this on GPUs and CPUs, or with a number of MPI options as well. So ARMX kind of takes care of the portability. Is a little motivation here. These are some slides from my collaborator Darren Huerta at Los Alamos. He's an MPASO developer. So we want to develop a hierarchy of regionally refined MPASO configurations. He does mainly on the U.S. Gulf Coast and East Coast. And so they've been working on these regionally refined grids. MPASO stands for Model Prediction Across Scales Ocean. So it's the ocean model in the DOE E3SM Earth system model. And it's unstructured, so you can have some regional refinement. And they've done some experiments using 30, 10, and 2 kilometer grids in the Gulf of Mexico to just experiment with the sorts of the resolution dependence of the processes that they see represented in the model. So the 30 kilometer config is consistent with the low resolution E3SM runs, 10 kilometer with high resolution E3SM runs, and the 2 kilometer one is like an ultra high resolution. Really these ultra high resolutions, you can only do regionally refined, and you can only do sort of like one component of the Earth system alone. Like these are ocean only runs. So let's see what they look like. The 30 kilometer one isn't even shown here because it's quite coarse. But here we can see a comparison. Excuse me. So we're missing. So the 30 kilometer one is sort of missing some basic dynamics like the evolution of the loop current and the eddies. So we're not even going to show that here. So let's compare sort of the two more interesting runs: the 10 kilometer equivalent to the E3SM high resolution configuration, and the 2 kilometer. Can you see my mouse, or do I need to turn the laser pointer on?
Don't see it.
Okay, let me make a laser pointer then. How about now? Yeah. 10 kilometer, 2 kilometer. Can you see my laser pointer now? Okay, good. So let's compare these two simulations. So the 10 kilometer run has a loop current, Gulf Stream, loop current eddies, and some mesoscale activity in the Gulf of Mexico. Looks pretty good, honestly. It has fairly strong fronts. This is showing the relative Caesarist temperature and the relative vorticity. And the relative vorticity is fairly strong. It's getting to be, close to F. Over here, though, when they extend this to a 2 kilometer simulation, you see that there's a lot more detail in these flows here along the shelf break, in the front of the loop current, and in these sort of features that are riding along the continental slope here. And you can see this really well in the relative vorticity, where the fronts are no longer smooth, but there's a lot of structure within the fronts. And so there, the relative vorticity is increased, so that the Rossby number is a lot higher now. So these are much more nonlinear features. So it's pretty neat to be able to achieve these sub-mesoscale permitting simulations, but these simulations are very expensive. So the current throughput, 96 simulated days per day using 12,000 cores. That's hard. One of the questions we got, this explanation, one of the questions we got in the review of our project and subsequently is, MPAS-O is unstructured. Why not just run MPAS-O at the high resolutions? Why not just, if you want to do an estuary simulation on the East Coast, why not just increase the resolution of MPAS-O until you can resolve that? And there's some problems with that. MPAS-O doesn't have, they're working on having different time stepping in different regions of resolution, but that's not working entirely yet. And it's just these high resolution simulations, even just the regionally refined simulations, are slow and expensive. And every time you double the resolution, you increase the computational cost by roughly an order of magnitude. You could expect a 4 to 8 time slowdown to achieve 1 kilometer resolution, and 1 kilometer resolution is pretty typical for modern coastal ocean simulations, and insufficient for estuarine simulations, even of like a big estuary like Chesapeake. So a lot of ROMS applications nowadays, modern ROMS applications, employ resolutions that are on the order of 100 meters to capture some of the scale effects, or finer. As Baylor mentioned, they went down to 5 meters in Narragansett Bay. MPAS-O is just not going to get there. So in practice, there are limits to how far we can refine resolution with MPAS-O. So wouldn't it be great to take an existing model that has been used for decades, 2 decades, to run regional applications and use that to pop in the middle of an MPAS-O simulation only when you want it? So that's the kind of the motivation for this study. And I wanted to also point out here that transition in the fronts becoming more, having more structure and becoming more nonlinear isn't really something that depends on the resolution of the model in terms of kilometers. This is really sort of, you have to think about the parameter space, the part parameter space you're in. And so this is an example from a course simulation in the northern Gulf of Mexico. So the Atchafalaya in the Mississippi are right over here. So this is strongly forced by fresh water from the Atchafalaya in the Mississippi. So it's very strongly baroclinic. And so you can see that on the continental shelf here, we get a bunch of eddies as the Mississippi River plume undergoes baroclinic instability. And these are, pretty energetic features with, Rossby numbers of 2 or 3 along the fronts. But as we go from a 1.5 kilometer simulation in this region to a 300 meter simulation over this region, you can see that the fronts all of a sudden become more energetic and get a lot more structure. So the same process we saw going from 10 to 2 kilometers in the whole Gulf of Mexico also happens at these finer scales under stronger buoyancy forcing. So I think this is a pretty pretty common problem, or a pretty common thing that happens when you go increase in resolution. And one of the reasons why we think it's important to think about fronts is, here's an example of, I've got a student, Dylan Schlichting at Texas A&M, who's still there after I left P&L. He's looking at numerical mixing in the coastal ocean. There have been a lot of interesting papers on numerical mixing in estuaries by Parker McCready, Hans Burchard, Rocky Geyer. And we've been thinking about how do we take these studies out into the continental shelf. So we've been looking at numerical mixing over these regions right here. And this is an example of relative vorticity. It's the same kind of figure I just showed you before. And this is an estimate of the numerical mixing locally based on a method by Burchard and Renaud. This is not the best method. It's a little noisy. And this is the absolute value of the numerical mixing, because there can be, you can have, we're looking at salt fluxes here because salt is the primary determinant of the density. You can have positive and negative values of numerical mixing. It's not necessarily always positive, but we're looking at the absolute value just to get an idea of the order of magnitude in this figure. And you can see that the numerical mixing is associated roughly with the fronts. You can see the features in here, and the numerical mixing is a significant fraction of the total mixing. So here's an example of the vertical mixing turbulence closure scheme. You can see that this is darker red than this is. On average, the numerical mixing is about 1/3 of the total mixing, and the total mixing is the prescribed mixing that's through the turbulence closure, the horizontal harmonic mixing, the KF scheme, the vertical, and plus the spurious mixing. The numerical mixing that's mainly due to the errors in the advection scheme, and that spurious mixing is about 1/3 of the total, so it's significant. And when we increase the resolution, we decrease the numerical mixing by about 1/3, and so that's good. So we want to think about that. And these features aren't exactly lined up. So here's a front right here. You can see that the numerical mixing isn't exactly lined up with the fronts. It looks like it's on either side of the fronts. And so it's hard to do exact property comparisons here. So that's a difficulty in the analysis. So we want to focus on fronts. So let me finish this here. So there's a paper by a former student and postdoc, Li-Shen Xu. He's now a professor at Shanghai Jiao Tong University. He wrote this nice paper in Nature Communications describing this very strong downwelling and then at the nose of the front, and very strong upwelling in the lee of the front that was modulated inertially by the inertial motions that happen in the Northern Gulf. It's driven by a nearly resonant sea breeze with the local Coriolis frequency, and yeah, so this little cartoon schematic is supported by both observations, high-resolution observations, and high-resolution numerical modeling, and it shows that there can be really active vertical motions associated with the front that are kind of periodically driven by the inertial motions. So the mixing can be intense and generate strong vertical motions. Of course, we know fronts aggregate plankton and other biogeochemical processes happen at fronts. But I think the main thing is that as the dynamics form fronts, these fronts are always driven toward the limits of what the model can resolve, and so they're really these are really challenging features to simulate in the models, and sort of deserve focus when we're thinking about different resolutions. To that end, we are going. One of the aspects of the project is to compare and contrast ROMs and MPASO, and to, for example, think about what would be the equivalent resolution between the two models. One is an unstructured. They're both C-grid models, but one is unstructured hexagons, and one is a structured, a structured curvilinear grid. And so it's not clear that 1 kilometer resolution means the same thing in each model. So one of the first things we want to do is figure that out. Let's see if this will run. Okay, so we're going to make a nice simple model of baroclinic instability in a channel. You've probably seen this 10 billion times in one form or another. The unique aspect to this particular simulation, well, first of all, I'm driving it very hard with really strong, like unrealistically strong salinity gradients over the domain. This is meant to be similar to the Northern Gulf experiments I showed you that would really only be over 100 kilometers or less. So don't worry that the salinity goes to 55. It's just all, we can just non-dimensionalize all that stuff to get the right part parameter space. But you'll see here that everything's jiggling a little bit. That's because I'm forcing this with a nearly inertial wind, a weak nearly inertial wind to start to generate some inertial currents in the upper ocean, and those inertial currents intensify the fronts. We can see that here. So I'm looking at a number of different simulations forced with different magnitudes of the near inertial, like it's 0.9 roughly f as the frequency. So the first moment, I'm looking at the first moment of the gradient of salt squared over the whole domain at the surface. And you can see that as we increase the winds from nothing, this is this red line here, increase the winds, there's a maximum in the mean salt gradient. And as the winds increase more, they decrease. And the way I take this is that for no wind, everything is behaving pretty well. There's not a lot of fronts. And as you start to increase the wind, the eddies don't necessarily respond uniformly to the wind. And so when they're moving, they start to kind of bonk into each other a little bit. And that bonking creates stronger fronts to a point, and then as the wind gets stronger, you just start to mix things through boundary layer, 1D boundary layer processes. And so there's this sort of sweet spot where you're driving the flow, but not generating mixing. And so we want to look at that as a key part of parameter space to focus on the fronts. Another aspect of the project, I should say that we've been doing this for, maybe 4 months now. So we're still in our infancy. I would love to show you more complete results. I'm mainly just showing you what we're doing, the direction we're heading. Is one of the other things we're looking at is a realistic domain. We picked this one as our first test case here. It's a small domain in the North Atlantic. This is a ROM simulation, limited domain ROM simulation by Harper Simmons, who's a co-PI on the project. This was originally done to look at the interaction between fronts and internal waves, and to look at how fronts can drive internal waves to the bottom of the ocean. And so we decided that we would like to pick this domain as the first domain we nest within En Paso. We picked it because, there's no steep bathymetry and there's no coastlines. And so we think this will be an easy first one to try. And then later on, we'll try to move to the US East Coast. Further in this effort to couple ROMs and E3SM, this is, we have tried to put this ROMs domain that I just showed you within the E3SM coupler MOAB. And so this is an example that this is kind of an extreme resolution change here from these coarse hexagons to these fine grids, but this is just an example of what we might want to do. We probably won't want to do quite such an extreme difference in resolution when we do this dynamically. This is just a proof of concept. We can take the ROMS grid and interpolate the En Paso results to the ROMS grid and get fairly good results. One of the things we found out is we had to do something that was globally conservative. If we did something that was locally conservative, the hexagons imprinted too strongly onto the ROMS grid. You can basically see the hexagons in the grid, and that's not good. So we have to think about global conservation using a bicubic interpolation scheme. And the last thing I'd like to tell you about is ROMS X, which is this new port of ROMS built on the AMRX software. This is done by Ann Almgren at LBNL, and Gene Sexton is a programmer there who's the main person working on this. It's going to be, ROMS X is going to be the same functionality as ROMS, but it will be translated to C++, and it will run, various different kinds of MPI. You can run it on, various different kinds of architectures, so you can use different sorts of GPU chips. And you get all this for free when you link to the AMRX package. One of the other things that will be an advantage over just Fortran ROMs is we'll be able to exploit fast parallel I/O that's provided by AMRX as well. Right now, ROM sends everything to a single. It doesn't use parallel netCDF. It uses single CPU, regular serial netCDF. So it's pretty slow. I/O can be a real bottleneck. And right now, we are at the point where we're able to initialize, basically able to propagate forward an initial condition. And they're working on the sort of the dynamical core as we speak. So they've got a framework, and they're going to translate the dynamical core. And so progress is pretty good on that too. And that is my last slide. So I will be happy to take questions.
Thanks, Rob. Great talk. We're a little bit short on time though, so if anybody has a quick question, we can do one question. One online, Justin Small, do you want to go ahead?
Yeah. Hi, Rob. Enjoyed your talk, and we're going to meet, I think, next month to talk more. But have you thought more about the feedback to the large domain?
Yeah. So that's a great question. I think that's an open question. So I can imagine that there are many things in our simulations that, like, I can imagine that, I don't know, 90% of the time or more than half of the time, you would want to use this in a one-way, in a one-way nested configuration, not a two-way coupled situation. And I just don't understand. I don't know what processes are going to scale up. I think, one of the ways in which we could, one of the ways I was hoping to move forward with this is to identify which processes are poorly represented and matter, and think about parameterizations. Because, if a process is important, think about that North Atlantic, domain. Two-way coupling over that tiny domain compared to the whole North Atlantic isn't going to get you very far, even if we identify processes that do scale up and affect the large-scale circulation. That's a problem, right? So I think probably the most effective upscaling will be in identifying processes that are impactful and need parameterization.
All right.
And one of them would be the injection of inertial wave energy along the front, sending that energy down and creating mixing in the abyssal ocean, right? That's like one process that you could imagine would be important to represent, and it isn't now.
Okay, thank you, Rob.
Thanks
Okay,
again.
I can stop sharing now. Okay, thanks.
All right, Deepak, are you ready? Go ahead.
Sorry, I started sharing my screen, so my name is Deepak Cherian. I work here at ENCAR. This is some very recent work I've been doing with Annalena Dettelmeyer, Gustavo Marquez, Frank Ryan, all of us at ENCAR, Dan Witt at NASA Ames, and Jim Moom at Oregon State University. Like I said, this talk is very work in progress. It's very rough. Feedback is welcome. I would love to hear what you think. The rough idea here is to evaluate vertical mixing in models using observational turbulence estimates in the tropical Pacific cold term. The model here is CSM, so I'll be showing you full-on 2/3 degree CSM model 6 and comparing that to instruments that record at 50 Hertz or 100 Hertz. So it's a lot of fun. They'll be at the equator, so kind of just a quick overview of why we care about turbulence at the equator. The equator is super special because this is 2 weeks of data average to show you vertical profiles. So the y-axis is depth. The first panel is the zonal velocity. So the equatorial current system, you have the south equatorial current flowing westwards at the surface, the EUC, which is more than a meter per second at depth at about 100 meters, flowing eastwards. These are measurements at 0, 140 west in the equatorial cold term. Oops, sorry. So this is a very highly shared system. Just how shared is shown in the next panel. So that's stratification n squared in blue and shear in brownish. And the point here is that the shear and stratification are pretty high. So n squared is sitting at 2 or 3 times 10 minus 4. It's definitely stratified. But the shear is so high that the Richardson number sits at 0.25, which is special. In the theoretical case, once you go less than 0.25, the system is unstable to shear instability. And so this is a cool result. They went out with their turbulence instruments, they stuck it in the water, and you find a lot of turbulence. And since then, that was in the 80s, since then people have figured out that the flow above the EUC is sitting in the state of what's called marginal stability, where Richardson number of 0.25 is kind of special as a stability boundary, and it looks like in the long-term mean, the flow is sitting right at 0.25. There's a very cool paper by Bill Smythe. I encourage you to read it if you're interested, where he argues that 0.25 happens because the forcing tends to increase shear, so it reduces the Richardson number. The turbulence acts to destroy the shear and increases the Richardson number. So once you have this competition between forcing and turbulence, you can hit the stability boundary. What does the turbulence look like? Also super interesting. So here's 2 weeks of data. This is the measurement of epsilon, which is the rate of dissipation of turbulent kinetic energy. You could rescale this to form viscosity, which is a quantity that's maybe more familiar. The key point of this figure is that there's a daily cycle. So that's 1 day, 2nd day, 3rd day, 4th day, and so on. There's a daily cycle. It penetrates below the base of the mixed layer, which is that top half line. Right? So it's a daily cycle of mixing, and it's below the mixed layer. And it's tied to the fact that there's a bunch of, the flow is pretty close to this shear instability boundary. The lower black line there is the core of the EUC, so you can see it's kind of bounded. It never ever goes below the core of the EUC, it's always above it, so that's about top 100 meters of the water column. Very, very intense turbulence, nearly all the time. This is particularly intense. It was observed during a tropical instability day. But this is the kind of physics that's happening in the observations. We care about it because this is a major component of how the ocean takes up heat. All of that turbulence is mixing and acts to suck heat out of the atmosphere to the whole town, dump it somewhere above the EUC, from where it gets moved off the equator to the subtropics. One way to see that is shown in this nice image I like from Ryan Holmes's paper, where he looks at diathermal heat transfer through 21.5 Celsius surface. This is kind of sitting just above the EUC. Oops. So that large blue, that's a lot of heat going into the ocean. And you can see that the cold term stands out in this particular metric. One thing he shows here, if you look in the bottom right panel, is how much is attributed to shear instability in that model configuration that was using KPP, and it's a lot, right? So most of that total in the tropical Pacific is coming from the shear scheme, which ties back to the shear instability observations I was showing. So data set. Jim Moos and his group have been really creative. They figured out how to put turbulence really fast temperature sensors on moorings and have been deploying them on Tau and the Parata array. So these are moorings that sit on the equator in the tropical Pacific, tropical Atlantic. The longest deployment of these instruments is at 140 West. They started in 2005, so it's 2023 now, so they have more than a decade of data. What they observe is, you get an estimate of chi, which is the rate of dissipation of temperature variance, so it's units of Celsius squared per second. You can rescale that chi with the temperature gradient to get something like turbulent diffusivity. You can make a lot of assumptions. You can go from chi to epsilon and then get from there to a turbulent viscosity. You can take your chi and again go through diffusivity and get to a heat flux, right? So in modeling world, if you were using KPP, for example, the K is an output of the scheme. It's used to get the heat flux. The heat flux divergence is then fed back to the model into your evolution equation for temperature. And so that's how it all closes. Here's what the data set looks like. So they're moored instruments. They sense at discrete depth levels. So look at the top panel. That's the coverage of 140 West, 23 antenna in the Atlantic. I'm not going to show you today. It's hopefully something we'll get to. But so here's the point. We have all of this data. It's a long time record, so it captures long time variations. There are lots of cool results that come out of this. One paper I particularly like is by Warner and Moon, where they have this very nice line in there somewhere. It says the ocean's microstructure, really the equatorial ocean's microstructure, is meaningfully organized in macroscale patterns. And in that paper, they tried to make the point that once you take all of this multi-decadal data set and start parsing it out by El Nino phases, you start to see consistent patterns. So if you look on the left, on the x-axis is DSST dt, on the y-axis is an estimate of heat flux divergence, right? So dj dz, they have averaged over El Nino phases, but in the sense that you're warming into El Nino, you're cooling out of an El Nino, you're cooling into a La Nina, and then you're warming out of a La Nina. And so you look at the dt phase, and you can show, at least from these observations, it looks like there is some meaningful correlation. The other interesting one is on this one. This is actually, I'll get to this one later. Maybe focus on the bottom right panel. So this y-axis is epsilon. So again, you could think of that as viscosity. The x-axis is the Richardson number, and this shows a clear difference between the La Nina cooling phase and the El Nino warming phase, right? That's half a factor of 3 to 5 in epsilon, and how much turbulence there is, even at the same Richardson numbers, which is super interesting. So something about the mean state is influencing the turbulence. So those were very small scale observations. They think they're organized in large scale patterns. We have climate models that we are hoping get those large scale patterns right. And so this is the hypothesis. To do well, we think that climate models must represent these these macro scale patterns of micro scale turbulence with some fidelity. And the question is, do they? The framework that I really like is this paper by Lodge and Gent, where they, at least one of it kind of tunes the KPP scheme to do really well in a global simulation. But they make this point about clean and direct comparisons. The way I understand it is when you create the new parameterization, you tune it to an LES or DNS. That comparison is clean because you can force your 1D mixing model, you can force the LES with the same forcing. Both the things can be made to spit out the same quantities, so you can do a very direct comparison of turbulence quantities between A and B. And so it's nice. Then you stick the mixing scheme in your global simulation, and then it becomes really hard because now you mostly end up comparing a simulated mean state like SSD to SSD. This comparison is not clean because you can't ever get the forcing exactly right. There's always errors. It's also not direct because mean state properties like SSD or stratification are not the direct output of a mixing scheme, right? It's an indirect comparison. So in this talk, it's still not clean. Forcing errors always exist. We can't mask the ocean, but we're going to try direct. The baseline simulation here is something Gustavo helped me with. So it's CSM, MOM6, 2/3 degree. I'm calling the workhorse at the moment. Z star, 65 vertical levels. I think the important bit there is that it's getting to about 10 meter spacing out above the EUC. So it's kind of coarse that way. We use this KPP, default settings with CV mix. I ran the first cycle with JRA 55 forcing. Oh yeah, and so the cool thing is I stuck in virtual mooring. So here we save output every R, which is basically we trace a time step along the tau mooring longitudes, and I output a bunch of stuff. So state variables, bunch of turbulence things, heat budget terms. So it's something like a mooring, and see whether we can do direct comparisons with the mooring data set. So that would be the baseline. I do only one thing. We changed 3 KPP parameters. These parameters were chosen by Dan Witt, so no AI, only natural intelligence. He ran 1D KPP, tried to tune it to his LES that he's been publishing. At a high level, what it does is lowers the maximum viscosity. We think the scheme was too diffusive, so we reduced it by a factor of 2. We effectively reduced the boundary layer depth. If you know, this is the bulk Richardson number. It's by default 0.3. It's down to 0.2, which makes the mix layer shallower. The real thing is also that we turn shear mixing on at higher shear. So usually it turns on pretty early. Once you hit a Richardson number of 0.7, it would start mixing. We let the shear get more intense down to 0.5. We make, these are somewhat arbitrary, but they worked well when compared to LES. So that's the main thing we look at. Anna, who's talking later, will also show you a version of the same stuff, but with 150 vertical levels. So 2.5 meters in the top 2. Let me try this. So first comparison, we'll try the mean state at 0, 140. In greenish, this one is the tau mooring. That's the baseline. So that's temperature, a vertical profile. The y-axis is depth. It's a little warmer. If you look on the right, that's the zone of velocity. So again, the baseline is a little weak. The shear is weaker. The maximum is weaker. That's good. We stick a new KPP terms. We do really well. We actually don't do 2 different temperature. We start to do really well on zonal velocity. You do really well on shear. Boosting the vertical resolution doesn't actually make too much of a difference. It looks pretty much the same in the mean state. So this looks pretty awesome, right? The EUC is a lot sharper in our simulation compared to what it used to be. Here's another mean state comparison. Now the left one is shear squared, so UZ squared plus VZ squared. Again, we're looking at vertical profiles. Similar story, you can see that the baseline simulation is a little low. Once you tweak KPP a bit, you do a lot better. So that was a factor of 2 difference earlier. Now we're doing really well on it. Similarly with N squared, we were pretty low earlier. We're all the way up, right on top of what the tau observations say we should be. This last panel is the median Richardson number. Remember, it should be sitting at 0.25, and all the simulations are pretty much there. So that's kind of interesting. But we tune these KPP parameters, and we can do better on these indirect comparisons. Right? Remember, I'm doing mean state. Part of the reason those parameters were chosen are looking at these stability diagrams. So remember, one of the key quantities here is Richardson number, which is N squared to shear squared, and the idea that we're sitting at a quarter. The left panel is similar to what's been published by Warner and Moon. The x-axis is shear squared, the y-axis is N squared. These curves enclose 50% of the observation. So you look at which part of the space the observations are sitting at, right? And then we think our model should be doing the same thing if you're doing fine shear squared. The different colors represent El Nino phases. And part of the paper is making the point that in El Nino phases, you tend to be in the lower part of this phase space, and for La Nina, you're kind of very tightly distributed in the upper part where you have high shear, high stratification. The baseline case, the first thing that jumped out was there was a lot of observations in this lower corner, right? So we have shear squared was too low, N squared was too low, and at high shear squared and N squared, we were moving off the diagonal, which is the Richardson number equals borderline. That's where the observations like to hang out, right? So we were moving off. That was systematic error. We change new KPP, we do a lot better. Not perfect, but we move out of this lower quadrant a bunch, right? Particularly this dark blue line in like the La Nina cooling phase, where you get a lot of strong turbulence. We've also moved rightwards towards that marginal stability boundary a lot better at higher shears. So this is a big improvement. Going to 150 vertical levels is very confusing. Something's off with that simulation, so I won't talk about too much. But here's another indirect comparison, but it's more informed by disturbance observations, and it's helping us to make choices and decisions about what to do. So now we'll try direct, and now it gets super interesting. These are time mean vertical profiles of various turbulence quantities. The first one's chi, the second one's epsilon. So chi could be converted to a diffusivity, which is the last panel here. In all of these, this green one is the observation. I would ignore the last point. I think something's wrong with it by the depth, so just focus on the top 100 meters. The point of this figure is that a lot of these lines lie on top of each other. Like, we're doing really well on time mean chi, we're doing really well on time mean epsilon, we're also doing really well on time mean diffusivities. This 150-point simulation is really weird. I could explain it later. But like, we're doing really well on time means, right? This was very surprising to me. But once you get to the medians, the whole story changes. All the simulations are, for example, an order of magnitude high in epsilon. So this is like, you hit the right mean, but the observations get to that mean by having a low kind of consistent state and some very high magnitude events. KPP is giving you a very consistent, constant mixing. So the median's kind of high, but it still gets you to the same mean. Yeah. So this is what's jumping out, right? The details are starting to matter. When I got into this work, I thought, oh, we just do the time mean and that should help us, but it doesn't. You have to get into details, and here's another one. Here's the annual cycle of heat flux. So this annual cycle of how much heat the colton is sucking down somewhere between at 50-meter depth. The green is, this one is the observation. And here are the models. They're not too bad. They're always offset up by about a factor of 2. Look at the phase. The models start sucking up a lot of heat in April, May, and June, as the observations start about a month later. It's not clear to me. Like, you know, it's the peak in June, July, August, September is usually associated with tropical instability days. April, May, and June, I don't know what's happening. So there's something there. And so what I'm taking away so far is that the details are important and are giving us clues as to what to look at, as to what's happening with the turbulence. We're kind of running out of time. But the one last point I would try to make is, again, about these details. So just focus on this first panel. This is just a distribution of chi. Or you can look at the distribution of epsilon. You'll see that those are the tau observations. Then you look at epsilon. Those are very different, right? So these are the Ollie averages directly spit out by the model, pulled from the observations and put on plot. And then as you know, a constant issue is like the climate model isn't really getting Ollie stuff out of, right? Like there are no internal data, so you're kind of missing a bunch of variants there. So let's go to daily, and suddenly these agreements look a lot better. Like chi looks amazing compared to the baseline. Epsilon is doing a lot better. Like this makes our scheme look a lot better. And so here's another detail that I didn't really appreciate when I started this work is how we choose to make these comparisons, and those frequency choices are really, really important. Like if you look at an Ollie, you would say, oops, sorry. You look at the Ollie histogram, you would say, well, this is just mixing too much all the time. But on a daily average, well, maybe you're not so bad. So what is the metric that matters? What is the metric that influences speed flux? Is something I don't have an answer for, but it's important to sort out. And so I'm almost done. These are just some different plots. So here's the EUC. This is the baseline simulation. The right panel is observation, left is the model. Oh, sorry, it's updating really slowly. So basically the changes have made the EUC a lot better. Well, they make it stronger. Better is hard. The mixed layer depth ends up being a lot shallower. I'm sorry, this is not doing a really good job. But the mixed layer depth ends up being shallow. Gustavo is very polite and said, yeah, it's not that good, man. Big Patrol thermocline, if you look at the difference at the bottom, does seem to be getting better. So, so these parameters make a difference. And how we choose them matters. And the idea behind this talk was to try and see whether turbulence data sets give us ideas for how to do better on those parameters. So yeah, I think I'll stop there. One last, this one's kind of cool. This is from a paper that's in review. It's a climatology by hour of day on the x-axis. The vertical differences are different depths. And it's a time history of epsilon. The colors are wind stress. So I think this one's interesting. It's been by wind stress, which is an input to the turbulence scheme. What's plotted there is epsilon, which is an output of the turbulence scheme. But it's from actual observation. So this is where, I was running the complicated model looking at the outputs. The scheme is tuned by running simple models and looking at the outputs. Here's one that I think we can do both. We can look at the wind stress that's kind of in the data and in the climate model, and we can look at epsilon directly and see where you're representing those patterns, right? But anyway, I'll stop there. I'm happy to take questions and feedback.
We just have time for one question. So, Peter.
As you pointed out, the equator is special. So have you seen whether these revised parameters improve things off the equator?
They become worse, particularly on mixed layer depth.
Okay, that was a quick one, so let's do one more.
There's one online.
Who is Griffiths? Okay, Steve Griffiths, go ahead.
Yeah, thanks for that. I'm not sure if this is quick, if it's too long. Just so the spurious mixing question, which came up before, also in a couple of contexts. Ryan Holmes' paper, a lot of the mixing that he is diagnosing is spurious, is what you call spurious. It's the numerical term. When you are diagnosing epsilon and all the connections to turbulence that you're measuring in the ocean, when you're calculating that from the model, are you somehow including the numerical term, which I know is hard to do, but how are you thinking about that?
Great question. I haven't thought about it too hard. We've definitely discussed it. In this, everything I showed you, I skipped over this. It's good you called me out on it. I just calculated the explicit bit that comes out of the vertical mixing scheme. That is more dissipation. So the way I've been thinking of it is this is an underestimate of how much the model is dissipating. And so if you're wrong, they're definitely more wrong than what I've shown you.
Okay.
Yeah. But yes, I would like to do that. But I haven't done it yet.
Thanks.
All right, thanks everyone. Brandon Reifel is next. Are you online? Can you go ahead and share screen?
Yep, can you hear me?
We can hear you, we can see you.
All right, let me make sure I share the right screen. And is it showing up in slideshow mode?
Yes.
And you have my mouse.
Yes.
Excellent. Thank you. So first, thanks, Deepak, for that great talk that really complements what I'm going to be talking about here. So I'm going to be talking about some work I've been doing to improve the representation of the tropical Pacific Ocean in the configurations of MOM6 that we run here at GFDL. Hopefully, I'll convince you that my title is true, that we have improved the upper ocean vertical mixing parameterization. So this is work I've done in very close collaboration with Andrew Wittenberg over the last few years. And I've also had a lot of discussions with Alistair and Steve, so I want to thank them for their contributions as well. So I want to jump right in. I've been focused on this, particularly motivated because of a specific bias that we noticed emerged in basically all of the configurations of our last suite of climate models. And this bias is associated with the tropical thermocline. So what I'm showing here is DTDZ from the Argo climatology produced from the Romick and Gilson data in the upper panel, and from our model force with JRA 55 in the lower panel. And basically, the thing I want to point out here is this very sharp steppy feature you see that emerges in our simulations in both the Eastern Pacific and Atlantic basins that is not there in the observations. This does occur in JRA force models, core force models, coupled models, so it seems to be almost certainly related to the role of the ocean here and not the forcing. So the goals of the talk I'm going to give here are going to be to basically try to diagnose the cause of the shallow, strong stratification bias in the Eastern tropical basins. We're going to do this by testing fidelity of the OM4 vertical mixing parameterization, so very similar to what Deepak was just talking about, and then applying a variety of changes to these schemes and testing the sensitivity of the tropical thermocline to these changes. I'm going to use the two strategies that Deepak referenced here. One is the large eddy simulation versus 1D models approach. And then the second part of the talk, I'll be presenting the results in ocean general circulation model. So again, I don't have to go through this in much detail since we just had a very great introduction to the vertical mixing processes in the tropics. But the main point to understand here is that the vertical mixing is characterized by this large diurnal swing in the stability and the turbulence, which is basically associated with the daily cycle of solar heating, and then is sort of a little bit special because of the fact that you don't have rotation and you have these constant sort of wind forcings, and basically the way everything sort of develops is you get this very large shoaling of the boundary layer during the day, which is again seen in the observations of epsilon here, where basically the values become very small below about 10-20 meters during the day, and then you get a very rapid deepening of the turbulent regions at night. This is sort of that deep cycle turbulence that, again, Deepak just described for us in much more detail. The main point I want to make here, though, is that it has been shown in at least one previous study that these processes should be captured by the mixing parameterizations that we are using in our ocean models. So we're going to be doing some tests here to make sure that we're capturing basically these processes in the mixing parameterizations we use in OM4. So the first approach I'm going to take here is I'm going to test this by comparing directly to some large eddy simulation models. The large eddy simulation output I'm going to be using comes from a recent study last year from Dan Witt, and a lot of, I think, other folks were involved in that who are present today. So fortunately, all of the output from this was made available with the paper, so I have to very strongly acknowledge and thank everyone for doing that, make it very easy to use. One of the sort of very nice things about this large eddy simulation model is that Dan has imposed these sort of large scale horizontal forcing from a regional model. So this allows basically the evolution of the LES over the 35 days or so that he runs the simulation to be realistic and representative of the conditions that you will observe in the field. What I've done here, which I think really is a nice complement to everything that Deepak just showed, is that I've actually implemented the capabilities into MOM6 now that we can run MOM6 in 1D mode with the exact same fluxes and forcing as the LES. So basically taking sort of the other avenue to compare the mixing schemes here. So in the talk today, I'm going to talk about how we're using this configuration to test the OM4 based mixing. So that includes the EPBL boundary layer scheme that's described in a couple of papers here, as well as the Jackson-Hallberg leg mixing parameterization, which is in the model to basically parameterize vertical turbulent mixing in stratified shear conditions. This model also has options to use GOTM, which is something I want to get back into the main MOM6 soon. And of course, CV mix KPP. I'm not going to talk about any of those today, but I have started looking at some of that. All right, so to answer the question, can the OM4 mixing parameterization reproduce the LES heat flux? I'm going to start by comparing this particular sort of time series snapshot of the vertical turbulent heat temperature flux from the LES simulation against that from the 1D model. So here's the result of the LES above, the 1D model below. You can see the 1D model does get sort of the basic pattern of enhanced mixing at night, getting down to about the right depth, and the reduction of the mixing during the day. To look at this in a bit more detail and a bit more critically, what I've done is I've taken the diurnal composites of these over the entire time series. So now you can see how this looks in the large eddy simulation. You see this sort of fairly persistent deepening of the boundary layer at night, and then a rapid sort of shoaling of the boundary layer during the day when the solar heating reaches its maximum. What I'm showing is the same diurnal composite repeated twice here just for clarity. And when I do the same thing from the OM4 result, we can see actually much clearer what the biases are in the parameterization. So basically, there's I would call a quite significant bias in the heat flux, the phase and the magnitude. So in particular, we have too much of this downward heat flux during the day. We're not quite restratifying the boundary layer. And at nighttime, we have kind of a bit too rapid of deepening. And particularly right at the onset of dawn, we get this large sort of coherent pulse in turbulence that emerges in the diurnal composite. I'm not going to get into the details of this, but basically the conditions of the stable forcing constraint turn out to be failing here because of the large variability with deep cycle mixing. Basically, I would need to modify EPBL to better account for when mixing is more dependent on sort of pre-existing conditions in turbulence. But the other thing to recall here is that this is basically a very good example of stratified shear mixing. And we have this other parameterization in MOM6 already, which is the Jackson-Hallberg leg scheme. And so that's simulated in the large eddy simulation. And just very quickly, if I just direct your attention to the diurnal composites, you can see the answer is quite clearly yes. It's a significant improvement over OM4, which I've now shown on the right. Basically, we are definitely getting that rapid sort of shoaling of the boundary layer during the day, and we're getting a pretty approximate simulation of what the LES is getting at night. I will point out there's a very rapid downward propagation of the temperature flux in the evening, which is it's basically related to neglecting a time tendency of TKE in the Jackson scheme. So this is something we're going to address in some future work. But going forward, this seems like something we want to be able to take advantage of in the simulation, the skill that the Jackson parameterization has here. So basically what I've done is I've revised EPBL to relax this equilibrium assumption, which then allows it to let the Jackson scheme take over for parameterizing the mixing in this sort of deep cycle environment. And I've done this in a way so that it's still able to skillfully predict the mixing at higher latitudes where this issue is not so prevalent. So now we are able to get sort of a full model that calibrates much better to the deep cycle turbulent mixing in the tropics. All right. So now I want to finish up by implementing this in our global ocean model. So this is the OM4 configuration. and asked the question of how the improved parameterization helps the model. So this particular configuration is a 1/4 degree model. This again is forced with the JRA 55 reanalysis. I'm running it from 1999 to 2008. I'll be presenting results averaged from 2001 to 2008. I have made sure that these approximately converge to the sort of climatology you would see if you ran it all the way out to 2020. By keeping it a bit shorter, I can run a lot more experiments. So what you'll see is I have done a lot of experiments to see what parameterizations affect the results in what ways. So the relevant model factors I'll talk about in this talk are the boundary layer and shear mixing schemes, as well as the background mixing. I'm not going to talk about the role of the restratification and submesoscale parameterizations. It doesn't turn out to be quite as important for what we're talking about. It is relevant. I'm not going to talk about resolution or vertical coordinates. So there are some other concerns related to the hybrid coordinate and its performance in this region. So everything I'm going to present is actually in a Z-star coordinate here, so we can avoid that. And there's other things I won't be talking about, but they are things to keep in mind going forward. Okay, so the first result I want to present is what happens when we implement this improved mixing parameterization. And what I'm showing you here is 3 panels. So in the upper left is the result of the original OM4 model. And we can see the bias from Argo now. So we're taking the dTdz of the model minus dTdz of Argo. So where it's red, it means that we have too much stratification. Again, this is sort of the signature of this steppy thermocline that I introduced at the beginning. And you can see it in the Pacific and the Atlantic basins. And there's also some sort of shallow thermocline bias in the Indian. When I introduce the revisions that I presented earlier, you can see we get some changes to the signal, but nothing too substantial. So I've actually compared these directly in the bottom panel. It does map onto the original bias we were looking at. We are reducing that surface stratification a little bit, but it is only about maybe 10 or 20%. So after sort of all that work to test the scheme, this was a little bit of a frustrating result. So we started to ask questions and test the sensitivity to some of the other model factors that I mentioned. Turns out the most impactful setting was, if I were there, I would take a guess, but I'll just give it to you. It was the background viscosity. So what I was sort of doing when I was looking through the configuration settings, I noticed that the background viscosity we have is 10 to the minus 4, which is probably a bit higher than it should be. And so I did run some tests where I've reduced it to a few values. When I reduce it to 10 to the minus 5, you can see we get a very strong change in the thermocline in all the bases. And I particularly am focusing on the response we see in the Pacific here. And when I take the difference now between panel C and what I call B here, you can see it maps very well onto the original bias. So basically, this eliminates everything that we saw with the steppy thermocline. Now we do have a shallow thermocline on the west. I'll come back to that in a bit. But just to answer the question of why this works, maybe it's not too surprising, but basically it's because of the effect that it has on the EUC. So the EUC stays a bit shallower, it stays a bit stronger, and it persists a bit stronger as we go east. This allows us to have more shear as we get towards the position where we had that steppy thermocline. This activates the shear mixing parameterization, which helps to then reduce that bias. All right, so the final thing then that I'm going to show is I spent a lot of time now asking how we might remove or improve this now shallow thermocline we would see if we went with this reduced viscosity. And the one answer that I found that tended to work the best was just to increase the background diffusivity. We use a background diffusivity that I think is 1.2 times 10 to the minus 6 right now. So that's in the result you see in the upper left. I've increased it everywhere. I'm only focusing on the results in the tropics here, so it's definitely not going to be something to do in a global model. But what we can see is the response it has on the tropical thermocline is to bring it down much closer to the observation. So sorry, I didn't mention this before. I should have the traces here were the position of the maximum dTdz. So the solid being the observation and the dashed dot line being the model, and you can see it comes down to about the right value when we change the diffusivity in this way. It helps a lot in the Pacific for sure, and in the Indian. The Atlantic, maybe it gets a little worse. So it's sort of telling us that just increasing the diffusivity everywhere isn't the right answer, but at least this helps guide us to the sorts of amounts of mixing that we're perhaps missing for one reason or another. Just really quickly, I want to say that I did also look at this in salinity. So this is now going from the original model to the final model. So the DTDZ is the maps I was walking you through the whole time. We see these improvements in all three basins when you compare to the original model. The SDZ, we see significant improvements in all three basins as well. Interestingly, compared to what Deepak just showed, when I look at the currents, we don't see such a conclusive result. It is nice that by reducing the viscosity, we have less momentum being pushed down below in the sort of the lower branch of the EUC here. So this is the original model in red, the observation in black. The currents were too strong below the peak of the EUC before. They're much better now with the reduced viscosity, but we do maintain a bit of a strong EUC, and it is perhaps a bit too persistent going to the east. So maybe going all the way down to 10 to the -5 was a bit too much. But anyways, just to sort of wrap up everything I've said, we basically use the LES to come up with a slight modification to the OM4 mixing so that it is able to accurately capture the tropical mixing processes and their sort of characteristics. And then when we implement this in the global model, we found that what ended up being the sort of most strong levers were the background viscosity and background diffusivity. So hopefully this at least helps to clarify the role of the vertical mixing parameterizations and guide these future improvement efforts. I want to make sure I really emphasize the point that I'm not proposing that we do use these other alternative constant background mixing coefficients everywhere. This is sort of a proxy now to hopefully guide better process representation going forward, since we can see it doesn't give the same response in all basins, and it won't give the same sort of responses when we go off the equator. And the other important point is just that we need to now evaluate the effect of these, especially the change in the diurnal cycle in coupled models, to better understand how this might project onto coupled atmosphere ocean processes like MJO and so on. So thank you at this point. I'm happy if there's time for questions left, and look forward to discussion.
Lots of questions. I'm going to go to Anna first.
Thanks. Hey, thanks, Brennan, for this awesome talk. I'm wondering about the effect that you get this big effect in changing the background diffusivity versus changing some things in the shear scheme. Does that implicate that we're in the shear scheme, we're missing a bunch of processes that would then be subsumed in the background mixing, and that maybe we should either extend the scheme or rely on the background diffusivity more to capture all these processes that we can currently parameterize?
Yeah, thanks. It's a really great question, and that's something that I've been thinking about. So I, of course, did go to our shear scheme and went and tried to look at various parameters, you know, the critical Richardson number and so on, to see if I could, you know, get better representation of the mixing in that way. And it turned out that didn't seem to be the role. So I think exactly what you're saying is right, which is that we're somehow missing something that's relevant to the mixing, whether that just has to do with maybe the sort of the high frequency of the processes, which is, you know, very, I think, complementary to what Deepak was just showing and saying. If, you know, it turns out that this is something that we have to account for with the background mixing, maybe it's something that we can justify in the short term, but hopefully we can come up sort of with more sort of process physics-based solutions for the long term, especially because you want this to be something that generalizes in a climate model. So, yeah.
Cool. Yeah, I wanted to talk to you. I mean, a long time ago, I asked Eric DeSero what the turbulent Prandtl number should be, and he said, well, it's the last number you'll ever know. So I wanted to know if Deepak had any update on that. And in particular, though, he did say it should be greater than 1 and less than 10. That was off the cuff. But you've put it to 1, have you not?
So I guess in my final configuration, it would become 1.
Yes. So
yeah.
that's just within his, maybe, but I guess there's no more progress on that, Deepak, that you know?
I haven't, I don't know.
Okay.
Baylor, quickly?
Yeah, so I'm interested that GFDL is now increasing diffusivity after they've worked so many years to decrease it. Do you have any evidence from other vertical discretization settings that helped inform this kind of thinking?
I should clarify that these are my results and don't necessarily reflect the opinions of everyone within the ocean division at GFDL. I think that my increase of the background diffusivity at the equator to 10 to the -5, it really helps in a very narrow band. So from like -3 to 3. Once you start to get outside of that band, I think it potentially can degrade the stratification simulated in the model. So we have to be very careful about how we might consider layering this into the existing parameterizations. So no, I don't have any great evidence for why it should be 10 to the -5. I think this just falls into the category of something that better matches the Argo observation. So it hints at something missing process-wise.
All right, thanks. Can you stop sharing so we can get Anna up? Thanks again, Brandon. Sharing.
All right. I can see my screen, so I'm assuming you can see my screen too. Hi everyone, I'm Anna. We've heard a lot about mixing just now, and so the main takeaway from this talk, big surprise, is going to be mixing really matters to not only one location on the equator, but I'm still going to be focusing on the equator, but also to impacts on the large scale system. And I want to zoom out a little bit and start by having another look at the tropical Pacific. So that's this region indicated here. We've already heard a lot about it. And you all know the tropical Pacific has cold temperatures in the east, warm in the west. And so this is our snapshot of 5 daily temperatures, sea surface temperatures of the simulation that I'll be looking at, which is mainly a 1/10 of a degree POC. So it's a little bit, it's before the MOM. We'll get back to MOM in the very end, and I'll also make another connection to Deepak and Brandon again in the end. But for now, we've been kind of thinking about the mean or maybe really diurnal short time scales, and I want to be focusing on a little bit of different time scales. So things you can see here are just now, obviously they're not coming. Yeah, there's the tropical stability waves that are passing along from the east to the west here, which will play a role, and we'll also be looking at the seasonal cycle of the system and how that impacts mixing and quantities that are influenced by mixing. Okay, so we don't need to spend a lot of time on this. You know the equatorial Pacific circulation by now. There's this really strong equatorial undercurrent that induces this strong shear, cold in the east, warm in the west, and then we have the SEC again really increasing the shear between in the water column with eastward currents in the subsurface and westward current in the surface. And then people usually look at the equatorial circulation and then draw this upwelling in the east, which kind of connects this idea of the circulation that we have. And the way that people draw upwelling is just sort of it's a vertical velocity, obviously, but it crosses temperatures. So I've indicated the temperature gradient here by colder temperatures in the subsurface and warmer in the surface. And so we're wondering now, how does that happen? And again, part of the message is mixing matters. I'll keep saying that. But what we want to do is we can decompose this upwelling into 2 components. And one of the components of the upwelling is the adiabatic component, in which the parcel doesn't exchange any heat with its environment, which really just results from the upward slope of the equatorial undercurrent, which roughly follows the gradient of the thermocline. So there's an eastward velocity component, but there's also an upward velocity component. And this upwelling cannot contribute to energy exchange of a parcel or any energy uptake or heat uptake. But when people draw this arrow, they usually don't think about this adiabatic component, right? We think about the diabatic component where heat is being taken up into the ocean. And Deepak has shown results from Ryan Holmes earlier, where you've seen this really strong heat uptake on the equator that really provides the global circulation with buoyancy. So this is a really important region to understand. And we're trying to understand the timescales on which this heat uptake by this upwelling, how that varies and what timescales play a role. So I have an equation to diagnose the diabatic upwelling, which is consistent of basically projecting the motion of a parcel into the direction of the temperature gradient. And then you also take into account the motion of the isotherm. So that's what's shown here on the left. Because if the isotherms move, then and you can move towards the gradient as much as you want, it's sort of escaping from you. So this is one way that we can diagnose from this output that we have diabatic upwelling that doesn't consist of any, it doesn't know of any parameterizations, it doesn't know of the physical processes. It's a standalone way to diagnose the diabatic upwelling. But we can also connect this equation to the heat budget equation. And this is really nice because it allows us to now actually attribute physical processes that are behind this heat uptake, that are behind this diabatic upwelling. And one of them is the vertical divergence of solar penetration. And I also really like that Deepak already said, it's the vertical divergence of the heat flux that really matters, because if less comes in than goes out, then you have a change of heat in the parcel. So it's always the vertical divergence of the solar penetration, the vertical mixing. For completeness, horizontal mixing obviously occurs in the heat budget. I will say I'm not showing any results because it's really small in this 10th of degree simulation. And then there's a covariance term, and that kind of arises because we have 5 daily averaged outputs. So there's some covariance that happens that might be a front passing along in these 5 days with changing temperature gradients, changing the dynamics of the system, and that will be captured in this covariance term. Okay, I already said it's 10th of a degree pop simulation. We have the heat budget available, which is nice because we can really calculate all these terms. We don't have to rely on a residual. So what does this diabatic upwelling look like in the long term? And now, again, you might recognize Ryan Holmes's heat uptake into the ocean. I'm just showing you a very narrow region along the equator here at 22 degrees Celsius, which for me represents somewhat in the thermocline. If we choose 21 degrees Celsius, the picture looks very much similar. And something that I was interested in, and this is kind of related because we're interested in understanding the spatial and temporal variability of the system, is what does that look like at different locations and in depth with the water column. So if you now look at cross sections of these lines that I've drawn here at 155 west, 125 and 110, and these are chosen because there's tow moorings there. So hopefully at some point we'll be able to do some observational comparison. You see that this diabatic upwelling, and this line here is the 22 degrees Celsius isotherm. So you see that this diabatic upwelling happens strongly located on the equator and then has this sort of V shape. And the region that we care about with this diabatic upwelling is the region in and around the thermocline, because that's where, if the diabatic upwelling and the heat uptake penetrates the thermocline, that means that it really connects the surface to something deeper in the ocean and not just something that you could think of as an isolated mixed layer. It's really taking up heat into the ocean. One more thing to point out is that when we are in the thermocline, we really can be thinking about upwelling, because remember, I've been projecting the motion into the gradient of the temperature, which means that we're not always strictly talking about a vertical motion, especially when we're really near the surface, because then we are actually in the mixed layer and our isotherms are going to be vertical, so we're going to be talking about off-equatorial motion. So that's another reason why I really want to focus on the thermocline, because we want to understand the upwelling in the system. And that's where it's most closely related to what people usually think of as upwelling. So I've promised you that we can, these pictures before, I've calculated them according to the left side of my equation, this projection of motion into the gradient with the movement of the isotherms. And now I can decompose, according to the heat budget, what this diabatic upwelling is due to. And you can see Very strong signal, especially in the thermocline. Again, the signal that I'm most interested in is driven by the vertical mixing component, the divergence of the vertical mixing induced heat flux. And then close to the surface, we get a solar penetration. So basically, because you have more heat coming in than goes out, because the solar penetration decays, you get this warming effect of the parcels, which leads to diabatic upwelling, but only really close to the surface, where it's really more of an off-equatorial horizontal motion rather than a vertical motion. So this is what it looks like in the mean. Again, we are also interested in looking at how this varies on different timescales. I'm not going to talk about ENSO. There's a paper, I think 2 years ago, about how it varies with ENSO. This is how it varies with the seasonal cycle. Again, shows a measure of the thermocline and showing you the diabatic upwelling in a map. You can see that there's some variability here. So it looks like, for example, in April, we have very little diabatic upwelling happening. And in July, we have a whole lot, which indicates that this heat uptake that is so important, again, for providing our circulation with buoyancy is happening mostly in this month and not so much in April. And we can now look again at the water column. So where does this happen, and what are, again, the physical processes that make that happen on a seasonal cycle? Is it the same balance that we also see in the mean? So this is the diabatic upwelling with temperature. I'm also, I forgot to mention this, I look in temperature space because I look at a transformation of temperature. So it doesn't really make a whole lot of sense to look at 50 meters, because at 50 meters, it might be different temperatures. The isotherms move up and down across Z space, and we wouldn't get a clear picture of where the action is happening. So I'm looking at temperature space here in the y-axis. And this is the seasonal cycle on the x-axis. And if you just sort of summarize these three different locations, you can see a pronounced seasonal cycle of this diabatic upwelling. There's two maxima. I don't know if you can see that on this screen. Maybe on your own screens you can see it. So there's a maxima early in the year that's higher in the water column. Another thing to mention is that this hatching indicates whenever an isotherm is present less than 50% of the time. That's a very steep function. It doesn't really matter if I choose 50, 70, or 80%. That just means when the isotherm isn't present, we're above the surface. So the closer you get to the hatching, the nearer you are to the surface. So you have this maximum of diabatic upwelling here near the surface, and then you have a sort of what I call an internal maximum later in the year. And what I've also overlain in this picture is some stippling here and some hatching dashes, stripes. And those indicate when, for the stippling, solar penetration dominates the diabatic upwelling. So that's, again, typically associated with more of an off-equatorial motion. And the dashes are when vertical mixing dominates the diabatic upwelling. And you can see that for all these maxima later in the season, they're really driven by the vertical mixing. That can be explained by the shear. I'm here showing you the shear, vertical shear in temperature space. So you can see that these maxima of mixing coincide with maxima in the shear. Again, this really is the shear-driven mixing drives this diabatic upwelling. This is, you can think of this as a motivation of why we really want to be getting this right, because that's an important measure that is connected to the large-scale circulation. It's not only important for the turbulence at this one location. And I'm showing you here the Hofmann-La of temperature. And I'm basically showing that to show you the thermocline is sort of roughly steady. And whenever we're looking at temperatures between 22 and 20 degrees, we're really thinking about this as an upward motion, because that's where we are in the vertically stratified region. And when we're looking at these maxima early in the year, again, driven by solar penetration, we're really in the upper part of the water column where it's just an off-equatorial motion. Okay, so that was the seasonal cycle. Now, if we move to subseasonal, the shorter time scales, you've seen these tropical instability waves, and they've also been mentioned before. Here I'm showing you a Hofmann-La of a year I have chosen that is representative. Other years you can find similar things. Of sea surface temperature, so you can see sort of these streaks here, which coincide with the passage of tropical instability waves, which are also indicated in these black dots, which are tropical instability wave kinetic energy. So when these dots are sort of further to the right, you can see the coincidence with these tropical instability waves. So we have them. What does it do something to the diabatic upwelling is the question. And if you look at the diabatic upwelling across an isotherm in the thermocline, you see here two things. You see the seasonal modulation that we've looked at before, very little diabetic upwelling in the earlier part of the year, more diabetic upwelling in the thermocline later in the year. And you also see these streaks. They're not as clear, but you can see there's some modulation. There must be some rectification of the tropical instability waves into the diabetic upwelling system. And if we now, again, decompose this into vertical mixing or a covariance term that would capture covariance on these sub-5 daily timescales, which you can associate to tropical instability waves, not because that's their timescale, but because they force a front to pass a region on very fast timescales. You can see the signal is mostly subsumed in the vertical mixing scheme, so there must be an enhancement in the vertical mixing that is seen from the seasonal cycle, but then also from these tropical instability waves. And an interesting thing is to look off the equator, where we are now a little bit away from this really strongly shear-driven regime. So we don't have this constant background shear that's driving this, basically constantly sitting at Richardson number 0.25. You see, again, tropical instability waves because they extend to the north. You see the signal in the diabetic upwelling, and now you see some of the signal explained in the vertical mixing, but you see a bigger part of the signal in this covariance of the front. So here, this is where really the tropical instability waves play a big role in modulating the diabetic upwelling. And that's something that we want to be looking into further. This is an overview to show you that the variance of diabetic upwelling, or the magnitude that it varies, really is the same or similar whether you look across the seasonal cycle ENSO or tropical instability waves. So this is diabetic upwelling in temperature space again, which means that all these processes have a contribution to variance of diabetic upwelling and therefore heat uptake. Something that I would like to do, and if anyone has great ideas, is I think it's really striking that you see this strong variance of the tropical instability waves, and they are clearly linked to A, the seasonal cycle, and B, El Nino, because they cure more during La Nina and less during El Nino. So a theory could be that maybe they rectify onto the variance that we see on these other time scales, and that's something that's really hard to tease out. So if anyone has any great ideas, please contact me. Yeah, so just a short wrap up that most vertical mixing really drives diabetic upwelling. Off-equatorially, we can really see the signal by the tropical instability waves. All timescales matter, and I just want to tie this quickly back together to the mixing talk that we've heard about before, because obviously these results depend on the mixing scheme I use, right? I'm using POP's output from the mixing scheme, and we know that that is biased. So if we look here at the seasonal cycle of sea surface temperature, published by Jim 10 years ago by now, and we look at the seasonal cycle of SST and POP in the simulation I've used, they're really similar. But if you look at the balance of what drives the seasonal cycle, the surface heat flux compared to the turbulent cooling, you can see that that's very different, or it's different for some part of the year in POP. POP gets some characteristics right, but then some are in some part of the year it's off. And this is something that we want to improve on because we want to get the correct answer, the correct SST, the correct representation of the processes because of the right physics that we put in. And we can do, this is sort of an analysis again of the mixing scheme, similar to what Deepak has shown you before. And actually Deepak has shown you this line for the MOM6 simulations that we have, which is again the turbulent heat flux cooling the surface. It really matters how you compare this, not only on timescales, like Deepak has said before, and whether you look at daily or hourly frequencies, but also on the choices that you make. For example, for this diagram, in order to get to the heat input from the surface, you subtract the solar penetration that gets below the mixed layer. And it really matters what choice you make there for your, for example, solar penetration function. By just changing these functions between what Jim Moon has used and what MOM uses, we can shift, in this case, the surface heat flux heating of the system, and then this diagram looks very different. So we're really trying to figure out what are best, ideally, you know, clean ways to compare these things to each other to optimize our mixing schemes and the performance of our models. Thanks.
Got time for questions?
We've talked enough
Well,
about
I have one then.
yeah.
And this is really going to be important to see if we're going to focus on the Pacific to know that we should. So I think that's really critical. But that last thing about the solar radiation surprises me
Yeah.
because I thought that Mom had overdone solar radiation because it took this Ullman stuff and it took observations and it really tried hard to do that. I thought much better than it need to be. Yet you're showing what Moon is using is completely different.
Yeah.
So there's a disconnect there somewhere because the blue line was based on ops, I believe. So that would be something to try and sort out. Now, the solar penetration does matter and we might as well get it right, and we know how to get it right if we know what right is. So if you could chase that down a bit, I think.
Yeah. Yeah.
Because that's quite different.
Very different. And it's also different from POP. I'm not showing here the POP one, which sort of sits in between the mom and the moon.
Okay.
Which was Olman. This is, I forget.
All right.
Yeah, Maritza. So, yeah, I agree. There's
okay
things to be looked at.
We do have a question online from Tony.
Yes, I just wanted to say that the attenuation of the shortwave penetration is also dependent on the biogeochemistry production. So it acts as a damping. So that's another part of it that has to be included.
Yeah, thanks. I agree. So for POP, we had a rudimentary implementation of that. So for all of this analysis that I've shown, we had a seasonal cycle of chlorophyll. And again, I probably should have put this function here. So basically the function sits in between, and then if you activate the chlorophyll, it varies the function, but the variance is very small compared to the big gap that we see. So basically, I don't know if you can see me, but the gap is like this, and POP sits here, and then chlorophyll makes it, you know, vary between this region compared to this. So, but we are currently running, or people are running, not me, this high resolution ocean force simulation with BGC. And I think it would be very interesting to look at how the variance of the chlorophyll is there and how that impacts the solar penetration. So I agree that that's an important point.
All right. I think we'll stop questions. Thank you, Anna, and all the speakers in the morning session. What time do you want to come back? Okay, we're going to do a full 20-minute break. Come back at 10:50. So 10 minutes before the hour.
I don't know.
Here, I think last year's EMI had a series of.
Okay, we're gonna start up again here. In just a second. Let people back online.
What are your regressions?
Okay, well, Greg is all set up. So we're gonna move from the thermocline up into the boundary layer, I guess, for the next couple talks. And, or maybe not, we'll find out. So first up is, let me say, we're about 10 minutes behind. Let's try not to get any further behind so we don't dig into lunch too much. But yeah, so first up we have Greg Wagner talking about some LES results, I guess.
Yeah, so yes, I'm going to talk about the development and calibration of microscale turbulence closure, which is it's a closure for vertical fluxes, especially in the boundary layer. That's based on convective adjustment and a prognostic turbulent kinetic energy, so we call it CAT. And I'm a research scientist at MIT, and I work working with the Climate Modeling Alliance. So the Climate Modeling Alliance is a MIT, Caltech, JPL collaboration to develop a new climate model, a new trainable climate model. And so what that means, what we're trying to do, I think the main innovation that we're trying to achieve is to automate the calibration of Earth system models, and included in that automatic calibration process would be uncertainty quantification of the climate model predictions. And we'd also like to leverage diverse range of observational data. So much more data than has been used in the past, mostly satellite-based with some in situ stuff. And we'd also like to utilize as much information as possible from high-resolution simulations like longevity simulations. So those are like the main two objectives, those first two, and I think all the scientists working on CLIMA, and especially my goal, I'm hoping that if we can achieve that second goal and develop an Earth system model whose calibration can be automated, which means we can tune many parameters at the same time rather than focusing on just a few when we do hand tuning. I hope that can eventually lead to improved parameterization of unresolved processes, like what we learn about what we need to do and accelerate that process. So some challenges of the project are the calibration. To automate calibration, it requires a lot of forward evaluations of whatever model that we're calibrating. So that could be single column model or global simulations, and that's very expensive. So it requires fast code, especially for global simulations. And if we want to calibrate single column models, we actually have to have a code that is also efficient in a single column context. So the software that we're writing needs to be flexible and fast, and it needs to be amenable to the development of parameterizations. So that's, it's very ambitious, I guess. But so to meet this challenge, so I work on the ocean component, and the ocean component that we're developing is called Oceananigans. And so this is, this Oceananigans is basically what we've done with Oceananigans is that we've in order to focus on parameterizations, we're using simple established numerics. So it's C-grid, finite volume, partial cell bathymetry, simple vertical coordinate. But it's written in the Julia programming language, which means that we can develop parameterizations. It's easy to develop parameterizations and plug them into Oceananigans. And in addition to that, it can run on a variety of architectures, including GPUs. So and that's crucial for performance. So on the left, I'm showing you a quarter-degree simulation of the global ocean. And with that setup, we achieve 3 simulated years per day on a single V100. And so that's the kind of performance that you get if you use something like 1,000 cores with OM4. So in terms of computational cost, it's very cheap. It's possibly up to 50 times cheaper, and that's like a crucial aspect for doing this automated calibration where we need to do large ensembles of global simulations. In addition to that, oceanarians can do large eddy simulations in either boxes with periodic boxes or closed boxes, and can also do large eddy simulations with complex bathymetry. That's something that was relatively recently developed, and it's efficient because we use a pressure solver based on Fourier transforms. So it has a non-hydrostatic mode, just like MIT-GCM, but it's much faster in its non-hydrostatic mode than MIT-GCM. And the bottom right is just showing you an example of how you can set up and run a simulation at the Julia REPL, which is like a prompt interface, and that's showing you what that looks like. So we also hope the Ocean is fun to use. So okay, that's all I want to say. So cat key is we have two boundary layer or microscale turbulence schemes in Oceanarians. One is a simple Richardson number based scheme that's sort of like Packnowski-Philander, and then but the flagship or the more sophisticated work is cat key, and so that's what I'm talking about today. And so the reason why we chose cat key as our basically our first parameterization to develop is because it was a relatively conservative choice. So cat key extends a widely used parameterization that was, I think the simple version was proposed by Blank and Delacruz in 1993. It's used by the NEMO ocean model. So it's standard, it's portable. You could implement it in almost all GCMs, I think, today. And we also believe that it has a wide range of applications. So it's not just a closure that's applicable for global simulations or coarse simulations, but we think that it has the potential to be used also at very high resolutions, down to sub-mesoscale or even crossing over the gray zone into near large eddy simulation resolutions. So cat key is sort of a standard model. So we improve on the state of the art in two ways. One is that we leverage the same calibration methods that we'd like to use for the global model to develop this parameterization in a single column context. So we use some sophisticated calibration methods to estimate cat key speed parameters and discover its biases. And then the second is that we do make some small improvements to the closure formulation that I'll try to describe hopefully. Which are measured, so they're conservative improvements, but they prove to be crucial, especially for reducing the sensitivity of cat keys predictions to resolution. So I'll get to that. Okay, so just briefly, I'd like to the talks that I would discuss calibration. So I have one slide about how we calibrate cat key. So the way that we calibrate cat key, the formulation we're going to consider formulations of cat key that have between 7 and 18 free parameters. So we use this calibration technique that can estimate all of those parameters at the same time. And this technique it's based on it's an ensemble-based method called ensemble column inversion, which we utilize between 100 to 1,000 individual single column models, each with a different parameter set in order to estimate the parameters. So the way it works is that we have like 100 guesses for what the parameters might be. And then we run the single column model forward. And then we use the discrepancy between the predictions of the single column model and our source of truth, which in this case are 18 large eddy simulations. And we use that discrepancy to update the parameter sets in all of those 100 models, and then we do it again. And that's so we iteratively improve on the parameters. And what happens is that through the algorithm that ensemble column inversion provides, the parameter sets converge to a consensus optimal parameter set. And I think one of the crucial things, a crucial aspect of this calibration technique is that it's what's called a posterior online. So when we're finding the optimal parameters, it involves running Oceananigans forward. And so because we use the predictions of the single column model to find the optimal parameters, we're incorporating things like numerical error and the details of the numerical implementation of cat key in the calibration process. The other crucial thing is that, and so the other thing that this allows us to do, in addition to incorporating numerical errors, it allows us to calibrate parts of the parameterization that we don't have data to directly estimate. So we can use indirect data as long as it's somewhat informative to calibrate parts of the parameterization that are not directly observed. So an example of that, is cat key's prognostic turbulent kinetic energy. So yeah, you might say, well, you actually can calculate that in the LES, and that's true. But the thing is that we regard the turbulent kinetic energy that cat key predicts as something that's similar to the turbulent kinetic energy in the LES, but it doesn't have to exactly be equal to it. Instead, what we want cat key to accurately predict temperature profiles and velocity profiles. So you can see in the bottom, the panel in the bottom left, that cat key, this calibrated version of cat key produces an accurate prediction of the temperature profile and the velocity profiles from the LES, but it doesn't exactly predict the turbulent kinetic energy. It's a little bit off, and that's by design. It's because we're not using that information to estimate the parameters. Okay, so that's how we do the calibration. Now, I'm going to walk you through the development of cat key by considering two different formulations of cat key. So the first I call minimalist. So cat key is a eddy diffusivity model. It's fully local, which is helpful. That makes it efficient. And it has a prognostic turbulent kinetic energy variable, which I call capital E. So the equation for that is in yellow at the bottom. And I'm showing, for example, how cat key predicts the vertical turbulent flux. So we multiply mixing length times the square root of turbulent kinetic energy to obtain an eddy diffusivity. And minimalist cat key uses a simple formulation for the mixing length, that's in the blue, and it has a constant turbulent Prandtl number everywhere and 7 free parameters. So, minimalist cat key is a simple model, but when we calibrate it to the large eddy simulations, so we use, sorry, and I should have mentioned, when we do the calibration, we're running a single column model forward, we're using 20-minute time steps for the single column model, and we're evaluating it at 2 different resolutions, 8 meter and 4 meter. So that helps us find optimal parameters that are relatively insensitive to resolution. But when we calibrate minimalist cat key, we find that its predictions, even though we're using 2 resolutions to calibrate it, the predictions are still sensitive to resolution. So on the right, I'm showing we have 18 different LES cases. I'm showing you one particular one that has weak winds and strong cooling. And you see in this case that there's 3 different single column results, with one with 2 meters, one with 4 meter vertical resolution, and one with 8 meter vertical resolution. And you can see that at higher resolutions, it's deepening faster. So minimalist cat key is simple, but its predictions are sensitive to resolution. In addition to that, it has no particular model for convection. So when we're cooling, like for example in free convection, and there's no other source of mixing, it has very unstable, unrealistically unstable buoyancy profile. So to improve on minimalist cat key, I have another formulation that I call favorite cat key, or maybe it's just cat key is a better name. And this one has 18 free parameters. So the way that we've improved on cat key, we've done 2 things. One is that we've replaced the constant turbulent Prandtl number with a variable turbulent Prandtl number. So now it's a stepwise function of the gradient Richardson number. And then the second improvement we've made is that we've added another contribution to the mixing length that is sort of like a convective adjustment scheme. If the buoyancy gradient is unstable, it cranks up the diffusivity. And it cranks up the diffusivity in a way that it estimates this convective mixing length. I think this is nice to show this at NCAR. I can't show my mouse, but if you look at in the yellow at the bottom left, you'll see that that's their scaling for the convective mixing length, where QB is the buoyancy flux at the surface. So some of you might recognize this as the boundary layer depth scaling that was developed by Deerdorf here many years ago. So we use this. So we use the information in the turbulent kinetic energy and the buoyancy flux at the surface to estimate the boundary layer depth, and then use that as a mixing length that acts during convection. And we find that, so all those embellishments add quite a few free parameters to minimalist cat key. So now favorite cat key has 18 free parameters, but we find that its predictions are much less sensitive to resolution. So on the right, I'm showing you 3 results from a case that has strong wind and no cooling. On the very right is the minimalist result, which you can see is sensitive to resolution. The 3 lines are different. In the middle, I'm showing you a version of CADKey that has no convective adjustment model, but does have this variable turbulent Prandtl number. And you can see that adding this variable turbulent Prandtl number improves things a little bit. The results are still sensitive to resolution, but much better than the minimalist CADKey. But then when we add this convective adjustment parameterization, the interesting thing is that we haven't changed anything that's explicitly associated with a strong wind case. But the thing is that when we add the convective adjustment piece, it allows the model to represent convection more accurately, therefore freeing up other parts of the model to, so there's fewer compensating errors, I guess, is one way to put it, when we have favorite CADKey, and that allows its results to be even less sensitive to resolution in the strong wind case. So it's showing you how, the minimalist CADKey has a lot of compensating errors, which means that it can't produce predictions that are insensitive to resolution. But favorite CADKey, by reducing those compensating errors, we end up with a model that's more accurate, even in a case that we didn't consider explicitly with the improvement that we made. Okay, so that's most of my talk. Here's the last slide. On the left, I'm showing you an implementation of CADKey in a 3-dimensional simulation, an eddying channel simulation that has some winds and buoyancy forcing at the surface. I think it's interesting, when we went to implement CADKey in 3D case, we found that the first way that we had tried to discretize the turbulent kinetic energy equation was had an instability. So we had to change the formulation, and then that required us to recalibrate all of CADKey's 3 parameters, and they all changed when we used the new formulation. But the results actually were quite similar, even though the parameters were different with the new numerics. So I think that was kind of a nice illustration of how we can use this automated calibration. If we have this automated calibration scheme, we can always go back and recalibrate when we obtain new information or change the numerics. In the future, what I'd like to do is I'd like to use a bigger suite of LES, maybe forced from GCM data that are more realistic, and also include realistic surface waves. The LES suite I had surface waves in it, but a simple model with a constant linear number. So what I'd like to do in the future is have more realistic surface waves, which will help motivate adding surface wave state dependence to CADKey's prediction. Also, maybe we implement in, I actually meant to write CD mix. Maybe got him to, probably not, but hopefully we can implement CADKey in CD mix. And of course, we would like to go to the global context eventually and recalibrate the parameters, maybe nudge them slightly to hopefully, and see what happens in that case, see if we need any more improvements or whether it works well out of the box. Okay, thanks.
Okay, we'll go with Deepak first.
Yeah, great talk. So when you're doing the calibration, what's in the objective function? Is it all state variables, or are you also doing turbulent stuff from LES?
I'm just using the temperature and the velocity field. Yeah, and as I said, we omit the turbulent kinetic energy, which you could regard. So that's regarded as sort of like a hidden variable of CADKey that's not directly observed.
Thanks.
Yeah.
Yes.
When we go to
Okay,
the
sure.
online
Yeah.
number. Steve Griffiths, go ahead.
Yeah, thanks for the talk, Greg. If you go to the penultimate slide, that's the one right before the end. Yeah, right. No, right there. Your convective piece in yellow, you have n squared positive. Do you mean n squared negative? So
that's right. Yep. Sorry.
Okay, so that helps clarify that confusion. The more speculative or more discussion question is the numbers you're getting from the learned parameters, the parameters you're getting that you're learning. Are you connecting them to some physical insights or physics at all, or are you allowing for the scheme to give you numbers that are outside of what you might think is physically relevant? How do you get physics into this scheme, basically?
That's a really interesting question. So I think there's a fear that if you do the calibration blindly, you end up with unphysical stuff going on. I think that if that happens, it indicates there's a deficiency in the parameterization. So we do have to put bounds on the parameters when we do the calibration. We have to initialize our guess. Basically, we have a prior, but I try to make the prior quite wide. I actually meant to mention that Out of the calibration, the minimalist cat key has a turbulent Prandtl number of about 1. But favorite cat key has a turbulent Prandtl number that varies between 0.7 and 2. So in a lot of aspects, the parameters that come out seem to reflect like what we think should be the case physically. But that's definitely something we need to keep an eye on as we go forward.
Thanks.
Yeah, thank you very much. This does give you some hope that we can sort a lot of these parameters out. But I go back to your statement about the large eddy simulation suite. Do you think if you have a realistic large eddy simulation that has a lot of variability in it, that you can substitute that for many simple, steady forcing kind of things, like a diurnal cycle?
Yes, I think you could do that.
So maybe you can get fewer LES, but more realistic and complicated would fill the parameter suite, maybe?
I believe so. Yeah, there's definitely, and you can even, the LES suite we've developed, we've been building it up. We had too few cases in the beginning and the calibrations wouldn't succeed. As we add more data, it actually makes the calibration much more efficient because the parameter values become more certain. I think with variable time varying LES, that will help a lot too.
Baylor?
Yeah, so Greg, first of all, it's great that you're keeping the numerics in the way you are in the calibration step. When diagnostic mode, looking at a variety of 1D models, we often find things like KPPs, both ends of the burst, the deepest and the shallowest, in different numerical implementations. And so the
numerics matters.
Yeah, it matters a lot. So that's critical to how it's done. It's not just the equations on paper, it's the equations the computer sees. But secondarily, would it be possible to predict a kind of tracer turbulent kinetic energy? I mean, because when you go and compare to observations and things, having some of the diagnostics that are similar to what's actually being measured, like TKG or epsilon, is actually a really helpful step in connecting to the outside of the computer. So now we're talking about inside the computer, outside the computer. It seems like you could carry one along, which is not CACI's, but it's CACI's vision of what the LES would probably predict, and it would have a separate set of parameters or whatever.
In other words, it should be useful that CACI predicts turbulent kinetic energy because you might be able to actually use that. It is a physical quantity, even though I'm saying it's hidden.
Yeah.
So I think that could definitely be an area of future research. Like, how can we improve CACI so that its predictions are still accurate, but it also accurately predicts TKE?
Yeah.
Or somehow produce a mapping between the CACI TKE and the physical TKE.
Yeah.
I think that would be useful. Yeah.
Okay, I think we need to move on. You stop sharing. Get Bill set up here.
Yeah, that's it. Okay, thank you, Frank, for driving here, because I don't have a license anymore. Yeah, so this is basically a development of the wavy ocean boundary layer that I've been doing with Gustavo and Alper, and would like to point out this is the same problem you've been hearing. You've given an ocean model and given the forcing and given the ocean state. What do you do with it? Well, the ocean model we're going to use here is the 2/3 degree. It's a Boussinesq MOM6, but we also have the wave average Boussinesq variety that was developed by Brandon Reichel. I believe the only thing I noticed turned off was the Stokes-Coriolis term, and so that's off. I think that's because you're not interacting the wave. Brandon can correct me. So we have two different ocean models. The forcing is standard stuff, the surface buoyancy flux and the wind stress from a JRA, but we also have a Stokes drift. And we prefer that as a forcing because it's not at this point interacted with the wave model. So then you have an ocean state, which I'm defining as buoyancy, and the O'Leary velocity, or the model resolved velocity, to differentiate it from the Stokes drift. So of course, what we want to do is compute a boundary layer depth H, and we've heard about that and how important it can be in some schemes, and the turbulent vertical fluxes of buoyancy and momentum. And then you have the vertical mixing tendencies, and that's all standard stuff. So that's just definitions and notation. Did I go the wrong way? Yeah. So that's what we're going to do, because in the I'm going to restrict myself to the boundary layer, which is a normalized coordinate between 0 and 1. It's, depth over h is sigma. And this is going to be consistent with some LES results, okay, as well as CV mix. I'm not ready to go and redo CV mix. So therefore the vertical flux or the vertical fluxes have to be written as a diffusivity, and a viscosity. And what I've done though is turn the coordinate system into an along shear coordinate and a cross shear coordinate. So it rotates with depth if you need to. Stays with the shear, okay? And in that way, you can see that you, like the buoyancy flux, you add this extra non-local term. You add it to the U, and you also then the cross stream. There's a momentum flux in the cross stream direction locally, and that's this gamma V. But because there's no gradient in that direction, there's no down gradient term. So it's this cross shear term that I'm going to play with and vary, and that's what I talked about a year ago. Okay, and since that year, I've taken a lot of time off and moved to other things. Okay, for now, I'm going to keep the non-local down or long shear or down gradient 0, because I'm just not sure what to do with it yet. And it's techniques like we just saw that might be able to eke out what that should be. Because doing what you just saw in my head, it took me 2 years to do. So I'm a lot slower than these machine learning things. So, okay, then you write it as a diffusivity and viscosity. So I'm just putting momentum and scalar so I can cut down the number of equations. And there's a turbulent velocity scale, the boundary layer depth, and this shape function. You heard about the shape function a bit yesterday. Now, the CD mix assumption is that these diffusivities are the same. That's an assumption, as is the actual functional form, because there's no real reason that these should be written as diffusivities necessarily. But if I'm staying in CV mix world for a while, so we're going to have that one. And the big things I'm going to play with is this turbulent velocity scale. That's all standard stuff. That's just the velocity times energy times length. You've seen that just in the last talk. And these are the two similarity functions. This is the standard buoyancy similarity function of the C over L, where L is the Monod-de-Broekhoff depth. But what you have to do when you have a boundary layer problem with another forcing, i.e. Stokes, gives you another similarity function. And that's this chi function of a wave variable to do with the Stokes effect of the waves on the turbulence. Okay, and those are the things I'm going to be changing, as well as this shape function. In addition, the limit on this velocity scale can vary, and I'll change that as well. And basically, this function of wave, this similarity function, is less than 1, so it's an enhancement of the turbulent velocity scale. And epsilon's defined to be between 0 and 1, 0 with no waves, and if it's only waves, it would be 1. So this is similar, this enhancement, to there is enhancement factors there now, except that it's different for momentum and for scalars. Okay, that's the only difference, and it's bigger. Then as far as the boundary layer depth is concerned, I can change the shear in the Richardson number calculation, resolve shear, and I'm also changing the fictitious shear due to turbulence that we don't know anything about. Now, where that came from is we know from convection that convection actually has no velocity. So this is 0. So you need something, and when you work it out, it has to be proportional to the buoyancy scale, velocity scale, convective velocity scale, which is minus the surface flux h to the 1/3 for pure convection. That's all you really know. Okay, so here are the cases. I take MOM6, JRA 1 run, and this is, I change the equation set. So from MOM6, and this is the 2/3 workhorse I learned yesterday. And these are the parameters that are sort of by default. A lot you've seen today have run this way. There is no waves at all, so that's 1. This is limited to 0.1 or the surface layer only. It's a cubic, that was mentioned yesterday, or fundamentally a cubic. VT squared is proportional to the turbulent velocity scale, which then defaults to W star only in convection. The Illyrian velocity is delta V, and this non-local velocity in the cross stream direction is 0, and there's no Stokes wave. So that's the control. Then I added the wave average Boussinesq equation set that Brandon sent over, and then I started to play with that. And as I said, the first thing I did was play with this. But then to make this consistent with the LAS, it turns out you got to change everything. If you change one thing, you're not being consistent. So I did that. What the LAS tell me is what this function should be. So I used that. Okay. I don't have a pointer. All right. Can I get one? Is that what that is? Oh,
Yeah, click on that. Yeah.
laser pointer. Oh, this is perfect. Okay, so I changed this, and that's the biggie. That's this enhancement factor, and that really enhances things. Okay? And then if I just go down, so what I do is I get a great deal more mixing with that term. If I go and change this, and like the LAS tell me, I don't need to restrict it. It's better fits if I don't. This is my, equivalent of the last talk. Again, it took 2 years to do. So then I pick that to 1, and that's what the LAS seems to do. This G function, and we saw some evidence yesterday that the cubic doesn't work very well. Well, that's absolutely true. We use a composite that's much less, and it's based on the LAS for oceans with waves. It's the same function, fortunately, both for momentum and scalars and whether you got waves or not, thank goodness. So I don't have to have an MS there. And that actually reduces the mixing. VT squared, I'll come back to later. Then what's been done before in what's called the legacy, you can actually make in the delta V term, which is down here in the Richardson number, you can make it the Lagrangian shear instead of just the Illyrian shear. This is this non-local, which is proportional to the component of the wind stress in the cross stream direction. And that works. That's what the LAS tells me what to do. And then this guy, instead of changing it and making it proportional to the turbulent velocity scale, I just do what I know. It's W star. That's the only thing I know. The rest to WS was an extrapolation and hope and a prayer. Okay? So that's the other thing I change. So if I do all those things, I have a case with WaveWatch 3 on the 2/3 grid. It's called the wavy case. And the other case I'm going to talk about and compare to is I just turn the waves off, which effectively turns off the wave average Boussinesq, and it makes this equal to 1. But I still keep the same GC, same everything else. So it is just the effect of these waves in this system. And that's what I'll talk about. So the first metric that I use is the winter halocline at ocean P because I know what it is. It should be between 120 to 180 meters is the thermocline. And this is an example of a whole JRA cycle. And you can see that indeed is where the halocline stays. If I just put those deepening or that one enhancement, I can take this to 350 meters in six years. Okay? And so this is the thing. And without waves, it's a little shallower. Okay? It shows up very clearly, and it's a place I've been to. I like it. I know what it should be. So it deepens, and that's what the waves do, and that makes some sense. And if I look at how the deepening goes and what it does in a sort of a more global sense, this is what it does to sea level height. Okay? And just a meridional section here. You can see what it does is it takes volume of sea level from the high latitudes to the equator. In both seasons, March and September, in all basins. These are the Atlantic, Pacific, Australia, that's just south of Australia in the Southern Ocean, and in the Indian Ocean. So that's what it does. Just putting in the non-local term used to change things in the east-west too. But this, when you put everything else together, I don't get that anymore. If I look at wave effects, which we've seen is just a mixed layer depth, this is the wavy case minus the calm case. You can see here's how much it deepens in both March and September. Winter, winter, summer, summer, and equator, equator. So it does deepen at the equator a little bit. I'll leave the equator because we've seen lots of it, but it's important, I know. You can see what it does in the lap C. Okay, that's an 80 meter in March, deeper mixed layer, relative to no waves. Okay, and you can see that there are changes in high latitudes. And these guys, you can see these increases here correspond to, if you remember back to Justin's small talk, he talked about the deep mixing bands. These are the things that get enhanced, both in the Pacific, in the south of Australia, and in the Indian Ocean. So my hope was to start looking at these more carefully, and instead of the equator, I'll move to the Southern Ocean. So this came from the paper that Justin referenced from Alice Duvivier, and she actually did a lot of Argo processing from the year 2004 to 17, and that's what the JRA is going through. So I do the averages in the wavy case of mixed layer depth as a function of latitude in the Indian Ocean at 90 east, and again at 158 east, which is in the Pacific, in the far west Pacific. And what you can see is, in fact, that relative to the calm, the wavy is deeper. But now what we have are these Argo floats. And what you find is that, in fact, sometimes the calm is better. Just because you're deeper doesn't mean you're better all the time. Okay, that depends on the whole ocean state. These deep mixing bands depend on the wind curl actually, not the wind speed. And so everything's got to work right. But you can see at 158 east, this is really shallow, the calm. So the deepening helps. So these effects, whether they're positive or negative, depend on what general circulation is doing and whatever and what have you. Now, what was found here is that these models that we were using always had this fresh bias in the Indian Ocean. Justin thought it was not enough salt coming from the Indian Ocean, and he says the IS has some of that too. So that complicates things. So you, instead of just looking at mixed layer depth, you really have to look at the profiles and the whole biases and lots of things. So if I look at an annual cycle, average annual cycle of salinity at 90 east, 40 degrees south. So now I'm going to a point, but I'm going to an annual cycle monthly. I can make some sense out of that. This is this very strange thing in the Southern Ocean of a deep salinity maximum. And that's what stops the mixing in the summer. Okay. And it's only when you start breaking through that in September, or depending when you break down, that's when you get the deep mixing bands. And the model actually produces this darn thing, believe it or not. And it's seasonally reforms, and it reforms all across the Indian Ocean, south of Australia, and into the Pacific. And this is what the wavy case does. So there is the Argo data at the mixed layer depth. So you can think of it's too crowded if I put all the lines on. So that's like the mixing in Argo there and there to go with the black, which is April, the blue, which is June, and the red is September. There's the deepening. If I look at the calm case, it's fresher. So what the waves have done, you've got a fresh bias, but the waves at least have been able to help mix up a little and sweeten it a bit, okay? Actually makes it salty. I guess that sours it. So that's why it's useful to look at the whole column, and you can do it on a monthly basis. If I look now at the Central Pacific, what the waves do, it's right on the Argo. The calm case, it's the other way around. It's actually got a bit too salty. See that? The model are over on the right-hand side of the triangles. That's model's too salty. This is right on. And you can go around the whole globe or the Southern Ocean at various points and see where this comes. Unless the point's really near a front and the model doesn't get the front and the right side, you can actually make this comparison. But there's one right at the front and the front's on the wrong side and everything goes nuts. And you can go into the Atlantic and make all these cases. And these are the biases. And so whether you improve or not depends on the bias you had in the first place, which is not just the vertical mixing bias all the time. And in fact, but then what I wanted to do is start going to points and actual field experiments and things like that. And then I found JRA wasn't good enough. In the Southern Ocean site, in the observations at the mooring, the solar radiation was never big enough to put it to go stable in certain days. And in JRA, it doesn't have the clouds and the solar radiation comes down and it makes it stable every day, which means you've got a diurnal cycle that's complicated, but it's not comparable to the observations and everything else we've done in the LES. At Ocean Station P, there's this case, it's beautiful in the data, and I was there, and it wasn't as hot as JRA says. JRA says it's so hot that at night, with a 20 meter per second wind, you've still got enough sensible heat flux to heat the ocean. Well, that doesn't happen out there, but that's so JRA isn't good enough to go on the daily scale. And I was trying to do that. However, I do have some Stokes drift from the Southern Ocean site. That's 47 south, just south of Tasmania. And we actually created, and this Lionel Romero, that's a very nice wave watch 3 works with the SOFIS winds itself. Okay, they sort of 5-minute, 15-minute winds. And this is the Stokes drift profile that he got. This is the wind direction. And then this is the surface Stokes drift. And this is 10 meters, 20 meters, 30 meters back down. And what happened here, there was swell coming from the southwest. And that's the southwest swell. The wind started to blow and blew at right angles to the swell and started to bring the surface, drag the surface currents along with it. And in time, these things just fan out very nicely. Okay, and you can see here that this U star over the Stokes drift magnitude here is 10 over U star, 10 U star. That corresponds to a Langmuir number to the -2 of 10, a Langmuir number a little bit less than equilibrium value, or a little bit more than the equilibrium value. The waves aren't quite built up enough. Okay, this LA to the -2 in equilibrium is about 11. But you can see it an order of magnitude drop by 10 meters. That's the shear. If I look at what WaveWatch does, is the WaveWatch that we've got now that Brandon put in breaks it into 3 components, and you get the Stokes velocity in 3 components at the surface, and then you have an exponential decay of each one. That gives you the Stokes drift. So I've taken these numbers and I can now use those anywhere in the code because I want to play with them. And that's what you get. And that is surprising to me because you can see how well there's the swell. It's there. Now it's WaveWatch with sort of big scale, so maybe that's not surprising. But look at this fanning as the wind goes. So this direction, it's got it with only 3 bands. And that's a pretty extreme case, so I can only imagine it getting better. What was surprising is the Langmuir number is now too big. Langmuir to the -2 is only 6. And that's surprising. I thought that that's the thing they could get, unless it's using the 3-hourly forcing of the model versus the 15-minute or 10-minute forcing of SOFIS. I just don't know why that's backwards to me. I thought the Langmuir would be right and the direction would be wrong, but that's what we got. So basically, I want to make conclusions. Yeah, we have a WaveWatch 3 surface waves have been coupled within the CD mix KPP construct to be consistent with the wave average Boussinesq equations, which the LES had. And so now at least the LES has the same equation set as the model. Okay, and it gives you this much bigger turbulent velocity scales in both momentum and scalars, but different. And we've got it. The Stokes drift with 3 components captures the depth decay, but for some reason the Langmuir number is about 30% high, and I don't know why. waves deep in the mixed layer and move water volume to low latitudes. And there's all sorts of other little effects here and there, but I just won't go through with you because my guess is that it's not that different than the original control experiment because many of the things we had in there largely compensated for the missing waves because we compared the data and the data had waves. Okay, you didn't have wind without waves in the ocean that I've ever seen. So, so in other words, that's why we had the bigger G sigma and it kind of worked. And that might be also why the VT squared, making it proportional to the velocity scale instead of just to W star, which is all you knew, might have been part of that compensation of error, which we just heard about. And that's a big thing. So I think that's why there's not so many differences, though there's still a little from the control, though it still tends to be a deeper mixed layer. Adding wave, so just adding a single wave dependency could double count in some instances if you're not consistent all the way through. And you're going to have all sorts of compensating things. Change the weight, change the equation set, change this. So I did everything. But wave impacts, were positive or negative, depend on the general circulation and forcing biases. And that's a problem. And that's why it's really good to see these people doing these couple runs now, because there's forcing biases and circulation biases all over the place. And there's, okay, the more observations we have from Deepak or anybody, so the parameters can't vary much, that would be really useful. And the sooner we find that out, the better. But we need cheaper waves. The 2/3 MOM6 with legacy waves run that was talked about yesterday, if you use Wave Watch 3, it more than doubles the time. So that's probably not what we need for this problem, though the wave people might need something else. It's pretty expensive anyway. It took a long time to crunch.
Is that Wave Watch on the 2/3 degree?
Yes, it is.
That's
right. Something cheaper. I don't know how, and I don't think we need it. And whether or not just more bands would give you that increased, change the Langmuir number better, or it's the frequency of the forcing, I just don't know. I was surprised. I thought they would get that right, because you just integrate the whole spectrum and give you those three terms. So that's the one thing I thought would be right. And it seems to be in the other cases I have also the same sign error. Okay?
Moved into questions. I go to Greg and then back to Taylor.
So I guess I'm not sure if you said it or not, but I think you identified at the end what I think is the right question, which is it's not, you know, whether waves matter for mixing, but whether the independent variability of the surface wave field means that it needs to be explicitly modeled to make accurate predictions about mixing in the boundary layer, right? So like that point, missing the waves were compensated for in original KPP. So it's like you actually were implicitly modeling waves and you did okay. So what is your conclusion on that? Like,
well, the biggest problem is you have a global model, so you fix it in one place, and if you're doing it with compensating errors, that compensation may vary from place to place, and in particular from time to time in a climate model you're going to. So the more physics you have right, less compensating, the better. And but basically, you're always going to be in that regime of trying to find it, but the less is better.
Yeah.
I mean, look at what they were doing to get that Labrador Sea straightened out. I mean, you'd really like to have some things that are fixed and well in hand, but that's.
Yeah. Yeah, the waves, the non-local aspect of the waves is totally missing if you're just parameterizing as a wind function. So, and that's like non-local in time and space. But so the question I have is back to the different Stokes profiles, which is, so, you know, the surface Stokes value is really unstable because it depends on how you're doing the tail off to infinity in the way that the subgrid scheme and the wave model works. So most of the closures actually don't use the traditional Langmuir number anymore. They use some kind of upper average or based on the surface shear or something to get away from that instability. Because it looks like the deeper profile of Stokes is pretty robust between your two estimates. It's just the surface value that's really off.
No.
And so I guess, but my bigger question after that was, what's the how now you have a profile of Stokes, how are you gonna use that in your similarity function?
Okay,
It
I'll
seems like
show
putting
you.
it in only as a scale.
But the first thing is you'll notice that you have the same drop. So the 10 meter is about a tenth the surface, just as the other wave watch. See, that doesn't reach 1 either. So it's about a 10%, it's a factor of 10 drop in 10 meters, regardless of where you started. So that the shear is off. What I do, okay, is I need the shear because I want to do the correlation with the turbulent stress over the surface layer. That is going to be right to the surface. That's why I need it right to the top. But I have an analytic form, at least, and I just take that analytic form and I can integrate by parts to get that correlation. And that's the production of turbulence due to the Stokes shear, which gets added to the production of, that gets compared to the production of turbulence due to O'Leary shear, and that's the wave function I have over in epsilon.
Right.
And it's the surface layer. Now, the nice thing about the surface layer is that the momentum flux is simply G over sigma times U star squared, because of the similarity theory works perfect. You know, you have the profiles and you can actually do that integral. So it's to do that integral, I need it to that's how I use it. I don't use a Langmuir number to anything.
But I guess my point is that the integral is not, the wave model can't predict that, and what the surface value it uses doesn't mean much, because it's all tangled up in like breaking waves and other things, and it doesn't do well. So when you tie yourself to that surface value, you're tying yourself to something the wave models really don't know how to do.
Well, to the shear there.
No, but if you do the integral.
It's the shear, it's the shear, that's right, that's right. So you think that this number from, these numbers from Wave Watch that look, these are really uncertain.
Yeah.
Is what you're saying.
Yeah, you shouldn't trust the surface value because it's very sensitive to a lot of parameterization choices. If you go just
okay, but
10
then,
centimeters below the surface,
but don't forget,
it improves enormously. It's
well, maybe we should think about what to do about that to make it more stable, or what I'm actually being given here. I mean, Brandon could tell me maybe he's not using the actual surface value either. I don't know, but that dictates everything.
Yeah.
So if that's not valid, then nothing is valid.
Yeah.
In this breakdown, if he's just giving me the surface Stokes components. So that's something we should discuss with him, because I need that correlation, and that's why I need the Stokes drift in with the turbulence calculations, because that's how the Stokes drift gets into the LAS, for example, is through this production of turbulence over the Stokes shear. And that's the important parameter that we've got to get right.
Okay, I'm gonna cut it off here so we don't fall any further behind, but we do have a little bit of a discussion at the end if people want to come back to these points right before lunch. So let me stop sharing here. Thanks again, Bill. If I can get my mouse to work, stop this. This thing is so sensitive. There we go. Okay, next up we have MoMA. Hell, are you ready, MoMA? Go ahead and share when you're ready.
I hope so.
Hear you, we'll see you.
Okay. Window screen. The noise and okay. You see the screen?
You?
Yes.
Good.
Is that a
Oh,
yes?
good. Yes.
Okay, good. Yeah, thanks for giving me the opportunity to talk here. And I think I can't see you. That's okay. I think Bill just said it right at the last point of the bullet. The last bullet point. We need cheaper waves, and this is something I did with Baylor over the last year. And it's a new way to model surface waves, particularly for the purpose of coupled climate models. And we call this particle and cell for fission swell, or pickles. And you can guess who came up with that name. It's
he's in the room right now and he's not here. So, yeah. So, and I think the end of the discussion just pointed to one of the main reasons why we should model waves explicitly in coupled models, right? Which is here the second point. Like the spatial gradients of the wave field are not necessarily the same gradients of the wind field. But the first one I want to highlight here is also there's the MIZ problem, right? Waves affect the Martian ice zone. And as sea ice gets more seasonal and thinner, waves will more and more affect the evolution of sea ice. And if you want to get that correct, you really have to propagate swell information to the sea ice. And for that, you have to explicitly solve like model waves. The other one was basically summarized well in the discussion before, right? Winds make swell, but then if winds change direction, there's still some waves there, and they will like impact a lot of things. Langmuir might be one of them. Others might be also this surface drag, white capping, other kinds of sea interactions. And then there's the third component, which is the area of wave current interaction. That's again in way smaller scales, right? We are talking down scales of probably smaller than 20 kilometers. And if models ever get there in a sufficient way, then we also have to deal with that, and then we also need explicitly model the waves. To understand the problem of wave modeling, we should start with observations, and this is a point in North Pacific Ocean Station, Papa. And there you have the situation that was also just described in the last talk, right? You have three swell systems superimposing there, right? There's a wind sea and two swell systems nearly going across of each other. And if you, to first order, want to describe this the sea state, you probably draw three red dots, and then you give each of them a direction, a peak frequency, and an energy. And then you end up with about 9 variables to get a first estimate of the sea state. What WaveWatch does, WaveWatch is able to reproduce this quite well, but it does a spectral discretization, right? It discretizes frequency and direction, and that leads to a large state vector at each grid point. And then at each of the grid point, it solves the wave action equation, which you see in the lower bottom. And that is one reason why WaveWatch is so expensive. And essentially, what we face here is this efficiency problem, the ratio between the red dots and the black dots. That's what we try to solve here. So what we propose is actually a medium complexity wave model. It sits right between spectral wave models from Hasselmann and friends, like from the wave modeling project, and second generation wave models like fetch laws. It sits somewhere here, right? And we call this back to the future because we take another term just before the innovation of the wave modeling project, and instead proposing something like a second generation plus model, which we call pickles for weird reasons. And what we do here, we will evolve the wave energy growth along Lagrangian trajectories, and then add to this iterative remeshing method such that we have information on an Eulerian grid. So yes, the main goal of pickles is trading accuracy for speed and convenience, right? We want to find another way to reduce this high dimensional state vector of the wave action equation, but still we want to be sufficiently accurate to describe like a kind of complex wave field. For doing that, we have to minimize particle interaction, to minimize the interaction between these blue lines here. We want to be very parallel because we want to run this hopefully on GPUs. We also want to model wind, sea, and swell because we need the swell to propagate it to the sea ice. And all of this will be written in Julia, or is already written in Julia, because we want to use the advantages of this language. For now, we ignore wave current and topography interaction, but that can be pretty easy added to that problem. Okay, how do we solve the system along a particle? Well, we solve the wave action equation, or in the simple case, the wave energy equation. And then the problematic term is this the divergence term here. And that one we write in the coordinate system of the particle, right? We go in the direction L and in the normal direction N. And the stuff in the L direction is what is responsible for the shift in energy, or for the growth of energy, and the shift in the peak in the group velocity, CG. Right, and that's for us a totally parameterless function, but that makes it way simpler. The other term, the divergence or the cross-term interaction normal to the rays, we ignore here, and we taken care of by the remeshing exercise. And what we then can write down is a set of equations for the particles, like that's a set of ODEs that can be solved very fast and independently. Then we have the remeshing part, which is based on particle and cell. Well, particle and cell is another way to solve Navier-Stokes-like equations. It was first developed by people in Los Alamos in the 50s and 60s, pretty much behind the curtain, but now it's widely used in plasma physics and electromagnetics, as well as some other geophysical applications. And it's very good in simulating shocks, like Berger's equation and so on. And we have these situations also when we have swell fronts propagating across the Pacific. The core of this method is this remeshing exercise. So you have a particle charge, in this case, this white dot. You want to distribute this charge to the nodal points, and you just come up with geometric weighting factors to do that. There are more fancy versions to do that, but we keep here this one for simplicity. And then we can actually assemble this model and create pickles. So we start with an ocean grid, whatever, an ocean grid point, like the gray dots here. And then we initialize the particle equations, the stuff here on the lower right. And I hope you see my mouse. And then we advance each of these systems individually, right? We advance these blue lines to a deformed particle state, so that we end up at these blue dots. And what we then have to do, we just have to remesh back to our grid where we want to have it. And that's using then particle and cell. But we also consider here conservation of energy momentum. And the way how we do that is we actually sum up energy momentum from the different particles within the domain, right? For the node here in the center, it would be all particles within this green area, such that the field state is then actually holding energy momentum. And then we just have to map back to the particle state, where we then can re-advance the model, and that's how that thing advances. Right now we're in the phase of reproducing fetch laws, or reproducing simple situations. So this is the classic situations of wind blowing offshore. Here's the shore. There's a constant 10-meter wind. And then the horizontal axis is here is the fetch, and the y-axis is time. And in the upper right, you see the static fetch relations that are just parametric functions that are trained by observation data. And that's basically the benchmark. What WaveWatch does, WaveWatch produces that quite well because it's a tuned model. And Pickles produces it also sufficiently well. But it's not tuned yet, right? There's a few parameters, wave growth and dissipation, that we have to adjust because the particle itself introduces a numerical diffusion that we then have to recalibrate. And there we just will use, what means just, but we plan to use the same algorithms that Greg introduced, right? Ensemble, common inversion. It seemed to work very well, and we can use that here with just bare bone wave buoy observations. Then what happens if you make dynamic winds or non-static fetches? I have here like an idler storm, because that's the process I like to think of, right? This is X and this is time. That's the Hofmüller kind of plot, and the storm moves from the left to the right. And in this process, it grows swell waves, and you see what you expect to see, right? This is the highest wind speeds here, at whatever, 20 meters per second. But you see that the highest wave energy, or the largest wave height, is displaced by that. You also see a second feature, which is this sharp frontier of the swell propagating further forward. And to illustrate what WaveWatch is actually doing, what Pickles is actually doing, it does this, right? So we initialize the particles at each of these black dots, and then we just advance them, and then we remesh them. And that's how it iterates forward. So this is I think at least a nice result, or that's like, it shows us a better way of the dynamics. Okay, then the last question is, how do we actually propagate swell? Because right now I just talked about growing the wind sea, but the sea state can be quite complex. Well, the answer is we just plan to copy the model and just do a second layer for swell and a third and a fourth layer for swell, such that the upper layer will be always the growing wind sea, and then there's other layers or other particles at the same node that live there, just that advect swell at the same time. Of course, you have to come up with interaction terms between these different layers. So one is when is the wave energy growing sea and when it is swell, but there we can just draw from existing literature about wave physics. Okay, and then here's kind of the money plot for this, right? That's an expected scaling for Pickles or Pickles perks, right? Because of the small state vector and the highly parallelization, we expect this thing to scale way better for increasing model resolution, right? So there are implementations of WaveWatch with CSM that are about 3 degrees and basically live on an atmospheric grid on like a 30-minute time step. And that's basically the limit what is allowed for the wave model to take up in processing time. But when you want to provide wave informations on the scale of CMAP6 kind of model, like on a quarter degree, then you will have to face 4 orders of magnitude increase of computational cost, right? And I'm not sure if you want to do that. Instead, if Pickles will be about an order of magnitude cheaper, at least. Depends again on the way how complex we do that, right? The lower limit is probably the black line here, which is just the stuff would scale with n, but it's also not particle-in-particle interaction or n-squared interaction. That's what we want to try to avoid. So we really think we will sit somewhere here. Then a few other limits about this model, right? We think it will work well up to like in this gray area, essentially, like up to like 5 or 10 kilometers. After that, like the dynamics you want to model really change. So we are actually not sure about that limit yet. And so maybe one word about what happens next. It's yeah, we will do the swell part next, I think, and deal with dissipation and dispersion and frequency, and then we will do a lot of testing against WaveWatch 3. And with that, I would take questions.
Questions for Mama? Brandon, got a hand up. Stephen, here's Griffey's. You're at the top of the list. Go ahead.
Yeah, thank you. I like that talk. One thing that I wonder is when we first started playing around with WaveWatch a few years ago, we realized that it was poorly written from a computer science perspective and not very parallelizable. And I'm wondering if the motivation to go to something like Pickles, which I think is based on lots of good motivation, would nonetheless be a bit less motivated if somebody would take the time to write WaveWatch in a better manner that is actually parallelizable and more efficient. Is that, do you have any thoughts on that? I don't want to sound like I'm critical of this work. I think this is great work, but how much better can we get WaveWatch?
Well, if you start to write a wave model from scratch, you better ask yourself if there's a better alternative. So it's the right question to ask. I don't know. I also know that WaveWatch, as it is written, is pretty bad for parallelization and coupling. For the limits of that, you have to understand the numerics better, and likely Baylor has a better answer for that than I have.
Well, as it turns out, Baylor has his hand up.
I was in response to Steve's question. So Steve, yes, if you look at this graph, so suppose you code WaveWatch and make it a factor 2 faster or a factor 4 faster. You could slide that WaveWatch line down by a factor 2 or 4, but you would never change the scaling law because the way that WaveWatch discretizes is the problem. We can, by more efficient implementation and going after the wave phenomena we care with a very low degree of freedom approach, we get on the blue line or the black line. And so it's a totally different scaling, even if you made the present implementation more efficient. I understand the DOE has actually made WaveWatch much more efficient and able to run on an unstructured grid now for impasse applications, but it's still WaveWatch, and so it still scales like the green line, not like the blue line.
So it's the CFL condition and the fact that you have a spectral discretization, I think. Right?
Kurt, you want to comment on what sort of a speed up you were able to get?
Yeah, we basically suffer from the same thing. Because of the spectral discretization, we can't go above, say, 300 cores. But as Baylor mentioned, I think there are some implementations based on spatial domain decomposition, but that's for unstructured grids, not for structured grids that we use.
Bob Holbert, you have your hand up. Go ahead.
Yeah, I really appreciate you're trying to find this kind of sweet spot to capture the wave effects. One thing, though, that strikes me with WaveWatch, if you try to coarsen the resolution, you get things kind of like this so-called garden sprinkler effect, where things tend to go in well-defined directions. Is there anything analogous that you're kind of fighting here when you're trying to design an optimally coarse resolution, or is this something that by design you just don't have to worry about? Thank you.
So the remeshing is a smoother. So I think I don't get these numerical artifacts of the sprinkler. We discretize direction, right? So there's a glimpse over this part where you do this layering aspect, and that's really the question how well you understand wave interaction. So the the wave interaction, how you discretize, how you make these rules, right? And that will be a kind of an artistic jump to do that consistently. So that's the limit there. I don't know how good we will be. Yeah.
Greg?
I want to make two comments. One is that it's so all those parallelization issues might be less of a concern. Going far into the future, if we're using GPUs because we use far fewer nodes in those configurations. So, but that doesn't affect every model, obviously. I guess the other, I think the moment we've talked about this before, but I just want to raise the question here: is there any way to do you see it as possible to simplify WaveWatch in a different way, like reduce the spectral discretization, but somehow introduce some approximations that allow you to have so you can have less frequency wave number bands, which help solve part of the problem, but still have no layering representation.
I know we talked about this before. What is your question? Is there a way to make?
Do you think that's a fruitful avenue of research or not?
Can you repeat?
Do you think that there's also a second generation plus type model that's Eulerian, but rather than discretizing in frequency space, you use some kind of like bulk representation? It's still right. See what?
Yeah, no, I don't think so. Because waves are not a fluid, right? It's a highly directional thing. The stuff goes only in one direction, basically. And that's what makes it very hard to do a purely Eulerian thing that also accounts for the wave physics sufficiently. I cannot imagine. Maybe I'm just too stuck in this particle idea already. But I don't think there's another second generation plus version to do.
Okay, thanks. One more quick question.
Are there any software engineering complications coupling something written in Julia to climate models that are not written in Julia?
I don't know.
I think there's work. Yeah, there's people out there. I think people are trying to work on like calling Julia from Fortran or compiling Julia to some kind of static binary that you could call. That is possible, but maybe not possible today.
Okay. Thanks. Okay, we did have some discussion time here, but we've hit the 1 hour. Any other pressing questions at the moment on boundary layer or mixing questions? We've had good discussion through the meeting, so I think we're good. So we will break for lunch until 1 PM Mountain Time. We'll have, this afternoon, we'll have some of the scale and mesoscale on the table. We'll see everybody back at 1 o'clock.